tell us to start. Okay, so the computer has granted us permission to start. Good morning, everyone. Oh, I'm not sharing. Okay. Share. As you can see, I'm happy here today. The sound is working. Everybody's happy. Okay, so I'm going to go over a very brief overview again, what we're doing in NG East is we're developing GMPs for magnitude 4 to 8.2 moment magnitude, and they have to span a range up to 1,000 kilometers. So for PSA from 0.01 to 10 seconds, or FAS of 0.1 to 100 hertz. That's our project. So the people who are only joining today, if you want to hear more about this project, listen to previous workshop videos and you'll hear more about it. So just to make sure everybody's on the same page on what's going to happen today. So again, this is being recorded to be posted online as part of our SHAC and project documentation. We have over 100 participants in person and online, although this morning it's early and I see a bit less, so they're going to trickle in. Everybody in the room, again, please use the microphone and announce your name when you're presenting or talking. Keep discussions focused on critical issues, which brings me to the issue of who is quote-unquote allowed to talk in these meetings. The priority is to the TI team. We invite also the PPRP to ask questions and provide comments as they see fit, and all the proponent experts and resource experts. So if you're listed as an observer in the printed sheet next to the agenda, you're going to have your minute of fame at the end of the day as time allows, and you're always welcome to provide written comments to Norm and I, and we'll make sure these are addressed or responded to. Okay, so we want to keep focusing on critical issues, so issues that matter to Hazard. The presentations for everybody are due before the session starts, so at the break, if you haven't given your presentations, please give them to Sahar and Maisa, who are two overqualified helpers and volunteers on this today. Remote attendees have been muted already. Or no, they will be muted because otherwise we have all
the conference has been muted
going on. So you can raise your hand in the ReadyTalk app or use the chat to communicate with Maisa, or send her an email as well if you have an issue or question, something that you would like to share. And we can unmute you or just relay the comments. Okay, the agenda and additional info is available on our peer website, and that's it. So as I mentioned, let me see, where is the topics agenda? Okay, I thought I had a slide. Okay, well, agenda today is pretty simple. We're going to continue proponent discussions on the GMP median models this morning. So we have Chris Kramer is going to present, Vladimir Grazier, and then there's a whole suite of presentations on the peer model because it's a newer concept and it has multiple different parts that we need to share with all of you. And in the afternoon, we're going to start comparing all these models in magnitude scaling, distance scaling, and in our famous Salmon's maps. So be ready, think about it at lunch, get a lot of good food and energy because you need to stay focused. And after the break, for the end of the afternoon, we have the final punchline and happy topic of Sigma. And Linda will present everything that is happening with the Sigma working group and proponent models for Sigma. Okay, so we're ready to start, and Chris Kramer is going to be our first presenter today.
Thank you, Christine. This is work I've been working on with a graduate student who's a couple of graduate students. Is that loud enough? A little closer. Okay. Or louder. Yes. Okay. A couple of grad students have been helping with the Naeem Al-Noman and Philip Agueno. Basically, we're looking at trying to develop an empirical DNA model, and this is an update on our progress on that. As a summary, by combining intensity-based estimates of ground motion with the NJ East ground motion database provides observational coverage from around magnitude 2.5 to magnitude 7.7 over a distance range of less than 10 kilometers to 2,000 kilometers. The intensity-based estimates do help constrain empirical Eastern North American GMPEs above magnitude 6, where ground motion observations are lacking. But it does so by providing a greater uncertainty. Also, our initial model that I'm talking about today is a linear geometrical spotting model, and we're looking into improving it, and I'll show you why we think it might be an improvement, using a bilinear model instead when we use the converted intensity information. Overview, basically, I'm going to talk about briefly the data sets used, how we developed the empirical GMP, and then present some results so far. Data sets used is the NJ East ground motion database from earlier this year. We used the ROAD D50 5% damp flat file. We add to that the 2001 Bhuj, India 5% damped observations, and we use geology-based VS30 estimates in order to have VS30, because we have a VS30 term in our relation. We're also using magnitude 6.2 to 7.7 historic intensity observations converted to ground motion estimates, and for the VS30 estimates at the site are done through Wald and Allen 2007 via their online tool. When we add this is the epicentral distance versus magnitude plot showing the coverage that we have. The red is the NJ East database. The blue up above magnitude 6 in a couple of spots here and over here are mainly Bhuj and Ghazli and also Nahani. And the black dots are where we are using intensity data converted to ground motions, and I'll explain how we do that shortly. So we get better coverage above magnitude 6, still a little weak, less than 40 kilometers distance, but hopefully this will be an improvement. Database, I went backwards, sorry, I did that, okay. Ground motion data selection. We avoid the Gulf Coast and western U.S. high attenuation, so we select stations and events north of 35 degrees north latitude and east of 100 degrees west longitude. We do include the 6.9 Nahani, the 6.8 Ghazli record, and the data from 40 kilometers outward from the 7.6 Bhuj earthquake. Intensity data selection. This is, since I last presented in July, we've come up with a new conversion of ground motion, intensity to ground motion relations that we've just developed. And as part of developing this, we are correcting between community internet intensity observations to MMI, and I'll explain that in the next slide. We've also checked the conversion using the 1988 5.9 Saguenay earthquake and the 2011 5.7 Mineral, Virginia observations as sort of a form of getting some ground truthing, hopefully, in what we're coming up with. We've also, as I mentioned, selected the intensity data from greater than magnitude 6 observations to include. Okay, CII to MMI conversion. There are differences between these two, as particularly pointed out by Sue Huff in a paper in 2013, that's the most recent one, in a presentation in 2014. We correct the ENA CII values to MMI using the difference between Bakken and Hopper 2004, which is representative of an MMI intensity prediction equation, and Atkinson and Wall 2007, which is representative of the CII intensity prediction equation. This was suggested by Sue Huff, and this correction is an additive correction. We do limit the difference between CII and MMI, the conversion to 0.6 MMI units close in due to unreasonable differences between exponential IPEs close in, and this is based on figure 6 of Huff 2013, which shows average differences of 0.3 to 0.5 MMI units, depending on the data selected on that plot, and those averages are our own calculations, not Sue's. So we can't blame her for them. Okay, we've developed these relations. We convert the CII data to MMI, add it to the older historical MMI data, where we have some measurements co-located with ground motion observations. This is for log PGA, it's base 10. What we plot here is for each intensity, the mean log ground motion, and it's fading again. Okay, I'm pulling away too. I'm thinking I'm screaming when I'm not. Okay, and we, particularly at PGA, it looks like we have a nice relationship here. There's very little data. There's only about 5 up at intensity 7 bin, which is 6.5 to 7.5, and 1 at barely into the 8 after the conversion. So I just show it on the plot, but we don't use it for fitting the curve. We use from 7 down to 2, avoiding 1, although intensity 1 looks pretty good here. And we come up with a relationship between that we can use to convert MMI to ground motion, PGA in this case. We've also done the regressions the other way, and they're pretty close to being, you can take this one and you get almost the same thing as regressing the other way. So they're fairly, I think the term is orthogonal relationships, but I'm not sure about that. But we are interested in going from ground motion to from MMI to estimates of ground motion on the historic earthquakes, which are MMI values. We use this is our trying attempt at ground truthing using the 1988 Saguenay earthquake here, and we're plotting the converted MMI values to median ground motion at the median distance for the intensity observations. That seems to do pretty good both in Saguenay and the Mineral earthquake. The Mineral has the MMIs, these are MMIs converted from CIIs. They seem to do a pretty good job, and this is true at very short periods. At longer periods, we discovered a bit of a problem. As you can see here closer in, the tendency is the conversion overestimates ground motions at closer in distances, which correspond to larger intensities. We looked at this in terms of the residuals. This is log observed minus log calculated base 10. And we see that there is a trend with distance out to 600 or 800 kilometers, and then it seems to go flat. So it is important to correct for this trend, which we do, but we don't project it out along, or you end up over-predicting ground motions at larger distances. So we've calibrated this and applied it, this ground motion correction. And then when you look at the 1 second data, it does look better, particularly for the mineral event. It looks more reasonable. So that's sort of the procedure we use to convert MMIs to ground motions estimates. The historical earthquake magnitudes we use for the events, we use the magnitude 7s from the historic earthquakes, the Madrid events, and Charleston of 7.5, 7.3, 7.7, and 7.0, with a 95% confidence limit of 0.3 magnitude units. These results are in a paper that has just come available online and will be published in the December bulletin. Basically, this is looking at intensities at larger distances where magnitude dominates the estimates. And in a formal sense, we come up with these estimates, and they're clearly magnitude 7s with about these values on average. We've also used historical earthquakes with instrumental magnitudes. Grand Bank 7.2 in the 1925, Charlevoix 6.2. Use those intensity data sets. So, empirical GMP, our approach, what the functional form is, and some results. Our approach is two-stage regression of Joyner and Bohr. This provides both between and within event variability and also event insight terms. The functional form we use is basically log ground motion. Here we are using base 10 with a distance term and a magnitude term. The distance term is given here, includes a magnitude saturation on the geometric spreading term, the attenuation, and we've stuck here a VS30 term with a reference of 760 meter per second VS. Our results are probably better at 760 than at 3,000, but we use this term to convert to 3,000 to the reference used by NGA East. The magnitude term includes focal mechanism. Some of the data we don't have mechanisms for, so this is undefined focal mechanism, reverse, and strike slip. These are ones when it's that and 0 otherwise, so it's just each term applies singly based on the focal mechanism. And we also have a linear and quadratic and magnitude term. The distance, we started using epicentral distance because that's what we started with. The distance is based on a standard approach of using an H term for pseudo depth, and the data was not sufficient to determine what H was, so we fixed it at 10 kilometers. We also have a reference distance of 1 kilometer in here. And obviously the total uncertainty is the sum of the squares, square root of the sum of the squares of the between and within event variability estimates. Okay, as to results so far, this is a work in progress. GMPE versus observations, I'll show you briefly some at magnitude 7.6 level. I'll show you what we're getting out of the regression in terms of scaling of VS, magnitude, distance, and variability, and then wrap up with some comparison with other GMPEs. This is at magnitude 6 magnitude 7.6 at PGA, 0.1 second, 0.2 second, and 1 second. At PGA in 1 second, we do have the Bouge data here in the orange circles through here. The others are estimates converted from MMI. The green line is the regression without intensity data, and the cyan or light blue line is with intensity data. Generally, when we have some data like Bouge here, the fits are closer between with and without intensity data. The regressions, when we don't have actual observations, only intensity observations, the intensity observations do help constrain the regression to more reasonable ground motion levels. So what are the scaling we're getting out of this, at least for these periods? This is the VS30 term scaling here. Our reference is at 760. And depending on period, red 0.1, black PGA 0.2, green, and 1 second blue. This is the scaling we get out of our VS30 term, shown here with this reference at 760, as I mentioned already. This is magnitude scaling, and is at short periods, there's less of variation with magnitude, and at long periods, as you would expect, due to the moving of the corner frequency of larger events, we get more of a variation. This is just a simple decay between these 4 periods, showing with distance and the values we come up with. This is for magnitude 7.6 at the reference velocity of 760, our reference velocity, not NJ East reference velocity, with focal mechanism of reverse. The other 2 focal mechanisms plot similarly up and down from here, but they're close to these. This is the variability. As I said, from the intensity data being included, it's a little larger than what we get when we exclude the intensity. But there's the total residuals at these 4 periods. We're working this week and next week on adding the other periods so we can fill this in, but haven't quite gotten there yet. And then we have the within event and between event uncertainty estimates, just to give you some idea. And this is log base 10 scale over here. So comparison with other ENA GMPEs. I've selected, just for this comparison, the National Seismic Hazard Mapping Project alternative GMPEs for 2014 to show in this comparison. So we don't have so many there, it's hard to see anything. Our empirical is this black line here, tending to be a little high at large distances and to the low side at close-in distances. I have not labeled the other GMPs on purpose because I want to show where we fall relative to that particular range of GMPs. This is for PGA. For 1 second, we tend to be a bit on the high side with our empirical, and at 0.2 seconds, it looks more like PGA, a little to the high side at large distances, low values closer in. It's possibly, this suggests that if we had a bilinear instead of just a linear geometric spreading term, we might be able to bring the near-in distances up some. It's possible that that could be done. We have some data, pretty good data, into 40 kilometers, but the data may be sufficient, and as we all know from talks yesterday and previously, doing it empirically, the data may not be overly selective as to what the higher geometric spreading closer in should be. But we'll try it and see how it works, but we're still in that process of doing that. And this is at 1 second, which again shows similar trend, higher at larger distances. This is sort of in the middle of the group at closer in this particular case. So, in summarizing again, combining intensity-based estimates of ground motion with the NJE's ground motion database provides observational coverage for up to magnitude 7.7 over a distance range of 10 kilometers to 2,000 kilometers. The intensity-based estimates can help constrain empirical ENA GMPEs greater than magnitude 6, although it adds to the uncertainty because of the bigger scatter in the intensity data. And we will be looking into a bilinear geometrical spreading model instead of just the linear one we initially chose, and see if the data supports some sort of selection on that with a bilinear to maybe improve what's going in our empirical estimates at closer in distances. Thank you.
Okay, 1, 2, check. Yes. Okay, thank you. Questions for Chris? Yeah, yes. Sorry.
Hi, Chris. Will you have any recommendations for converting epicentral distance into rupture or joiner bore for consistency with use with the other ones?
We just use the epicentral distance. We could use the other distance measures instead of epicentral distance in the inversion, and we regress. We haven't done that yet. We're still trying to make sure we can get the intensity data to reasonable values and that they are a positive contribution, not a negative one, which they seem to be. But this is another outstanding issue.
Chris, this is Rich Lee. I was just wondering, building practices and construction materials have probably evolved over 200 years. So I'm wondering if the intensities of earthquakes that are 150, 200 years old might be slightly biased compared to modern earthquakes for your ground motion correlation.
That's always an issue, but building codes are lagging California back east. A lot of the observations that we use, particularly like in estimating the magnitudes, were actually based on lower intensities, which are basically felt effects by people and not damage to buildings. And here with the conversion, we are using the higher intensities too. Getting a handle on that, it's a good question. What sort of bias it might have. If you have a suggestion on testing it, I'd certainly be interested in that.
Okay, we had the last word next, and then
I just had a question on the depth term H. I think you took it as 10 kilometers.
Yes.
Was that just an assumption to get started?
It was fixed. Naeem tried to invert for it, and he said the results just weren't stable, so he fixed it.
Or do you think is that something that's still on the table, that you might look at some of the results presented yesterday? I think there were magnitude-dependent terms there, right?
Well,
it just seems like that's such an important parameter in the near field to control the ground motion that it's something you may want to...
We're trying to do this empirically, so if the empirical data doesn't tell us much, we've got to be honest and say it's not telling us much, unfortunately. But, we could fix it other than in different ways, and we could consider that.
Okay.
Vladimir Greiser. Chris, can you provide us a little bit insight on Bush data? Because what was available, just briefly?
Yeah, the Bush data is, for the most part, engineering seismoscope data. So they're basically peak values. We've used them as the peak values, the peak horizontal values. There was one instrument roughly collated with one of these seismoscopes, and they got similar answers. One isn't a lot to hang your hat on, but we published all this in 2003 in the bulletin, and the observations are what they are. In that paper, we compared them to then ENA ground motions at PGA in 1 second, and they look compatible. The results we're getting here, still, particularly at PGA and also at 1 second, they look compatible to our intensity conversions. But that's another source of uncertainty in the observations that we're using.
Thank you.
I'm loud. Okay. Sue Hoff is online, but there's an issue with unmuting her, so she asked us to relay the question. So I'm going to read. My question is, given that the historical magnitudes are uncertain to probably a full magnitude unit, what is the justification for using intensity data?
If you read my paper that just came out, we don't believe it is that large. If you use IPE conversion, intensity prediction equation, estimates on magnitudes, a lot of the data closer in is biased, can be affected, not biased, but can be affected by things other than magnitude, which is why we avoided that data in this particular paper and used just the further out data, basically playing on the fact that larger the magnitude, the greater it's further out it's felt. And actually if you look at the intensity 3 for these events in the New England area, from the Charleston, the range for New Madrid, and from Grand Banks, these distances are compatible. Charleston is slightly smaller than Grand Banks, New Madrid larger than Grand Banks in magnitude. This is a qualitative measure. In the paper, we do a quantitative measure, which I won't go into here, but refer you to the paper where we come out with the magnitude estimates and the uncertainty estimates. Also, the Grand Banks, we've extensively looked into the attenuation. There's a paper by another student that's been accepted to JGR looking at LGQ in this area, and basically this is Eastern North America crust, and the Q is quite compatible with mid-continent Qs in Eastern North America.
Rob Graves, and actually my question is kind of related to what Sue was asking, but given that there are different estimates for the magnitude, I'm wondering what the potential impact might be on the regression or the relations. If, for example, the magnitudes were 0.3 units smaller or 0.3 units bigger, how much might that change the result?
Yeah, I don't know off the top of my head, but it should have some impact because on the magnitude term.
Yeah, and given that uncertainty, I think it would be useful to at least have that or some results along those lines, just so that we could look at it and say, all right, well, this is, what the significance is, even if it's kind of a qualitative assessment.
Comment here. Oh, go ahead.
I'm just trying to write down what we're talking about here. He's running in random effects, so he gets an event term out, which effectively, if there's an error in the magnitude, it should map into the event term primarily, right? And so now the question is, how do those the intensity-based event terms compare? And then if you simply put in an uncertainty, you could just run this with randomizing those magnitudes. How much is your result changing, right? Is that what you're suggesting?
Well, I'm not advocating for one way or the other, but I'm just saying, for example, for the New Madrid events, what if the magnitudes for all those events were high by 0.3 units? And since those are really the only events controlling those large magnitudes, I don't see how that necessarily is going to be taken into account in the regression, because those are the only data points you have at those large magnitudes.
Other than the Bouge.
Well, yeah, that's true. But so I don't know how that works in the code with the mixed effects, but if all of your observations, I'm kind of generalizing, but if, say, if all of your magnitude estimates were high, then I don't see how that would get mapped into an event term. It would just say, well, that's just the way they are. As opposed to then saying, well, all right, let's adjust all those magnitudes. What if they were all 0.3, 0.5 units lower? It seems like that would potentially have an effect on the entire regression.
Can I add something there? Kevin, I was thinking about that issue. What may happen is the scaling will follow that event term. Again, if you randomize that magnitude, then if the magnitude is higher than average, then you're going to get a stronger slope. And so in the end, the effect might be on some larger uncertainty on the magnitude scaling, if it's a few events controlling that scaling. And that brings to mind something that as an alternative way of doing it. It might be, maybe I'm suggesting another method to you, and that's not proper, but try to use some other constraints on the magnitude scaling, say based on RVT, things of that kind, but have the level and the distance scaling be empirically based, but to some extent, and perhaps in a mixed manner, have some more constraints on the magnitude scaling.
Wait another year. That is a comment. So.
But it's straightforward to simply generate multiple data sets with randomized magnitudes. And now the question is, are they correlated? Because I think you said all New Madrid events are shifted up or down. That's really the question that we have. So should they be fully correlated for all of them, or should we just be saying they're a random magnitude? I think the suggestion would be these things are calculated in a similar way, so they're probably correlated, right? But it would be conceptually straightforward to generate multiple data sets, just randomizing a New Madrid average magnitude error, right? And say, okay, they're all up half a magnitude, a quarter or zero minus a quarter and a half, and just rerun the regressions, and how much do the slopes change, right? Okay.
So that would lead to a suite of models that capture okay.
A suite or the uncertainty on the magnitude scaling. That's really what they're trying to get at, is how well is that term constrained. And you could compare it, as Gabe said, to some underlying point source model or other GMPEs to see.
That's why the comparisons at the end, just to see how we were coming out, relatively speaking.
Okay. Is there any more questions for Chris? Okay, so we'll get our next speaker. Thank you very much, Chris. And I think we'll try to do a mic swap. Nathaniel. Sorry. Can you start this? So maybe, yes, a longer mic. Yeah, okay, let's try that. Thank you. You can have your mic back.
Okay, good morning. My model is slightly, I would say, different from classical approach to what most people are doing. This is why I will spend a little bit time just reminding you guys what are the main features of the model. Again, this model was developed first for Western United States, and this approach was applied basically to the Eastern U.S. data with same kind of ideas behind modeling of attenuation of ground motion. Now, what make it significantly different from Western U.S.? I'm sorry, I probably will repeat whatever people said before me, but basically there are not enough data to constrain this well, and there are only few data points in the near field for large events. And actually the only large event which is in the database is Nahani magnitude 6.8. Now, what are the basis for my Eastern model? The basis for my Eastern model, actually there are two versions of this Eastern model, and the basis are the two databases which are created by NGA East project at different stages. NGA East project database which was given to EPRI, and EPRI 2013 ground motions are based on this database. And also I used recently the database that Christine Goulet provided, and it's the most recent September 2014 database. But as a result, I ended up with two versions of the same model. Because my first idea was to discard completely my EPRI-based model, but I found out it doesn't make sense. I mean, it does make sense to keep it, for right now at least. Okay, and again, this is why kind of there are a lot of stuff different for East from the West. Okay, what are my main constraints for creating this attenuation model? It is okay, same functional form, basically same functional forms that I developed for Western U.S. And my first step was just to adjust this based on EPRI 2013 and SSHAC 2011, SSHAC et al. 2011. And also, I used some information, of course, like the ratio between Western and Eastern U.S. stress drops, and finally, as I mentioned, the two databases, NJ East preliminary, if I may say, or Chris Kramer developed, and the recent one. Okay, just to remind you what we are dealing with this is the, okay, I didn't care about small magnitudes. This is why I started from, the request is to do it for magnitude 5 to 8. I decided to start with 4, and this is why I discarded everything which is below 375. This is my database relative to magnitude rupture distance. Actually, I looked at larger distances, but main attention is up to 1,000. Now, this is how it relates to VS30. And the next one, which is very important, is this plot. It is VS30 relatively to SA. What I would like to underscore looking at this data, that there is basically no nonlinear cases in our databases. Because there are only two data points, if you can see, below 300 meters per second, which are 0.1 G and slightly higher. Basically, everything else is linear case, which will be important for me later for correction. Even I looked at nonlinearity also. But look, that's the point I wanted to make based on this plot. Okay, that's just a reminder. Again, why I call it modular filter-based approach, because basically, first I start with PGA, and PGA consists basically of multiplication of 5 different things. One of them is not used for Eastern U.S. basin effect, but I have it developed for Western U.S. This is why, in case if somehow we will have this to deal with, it can be plugged in, but it's not plugged in now. But basically, we have magnitude and style of faulting scaling, core attenuation, anelastic attenuation, and side correction. And of course, filters are different from Eastern Western U.S. Now, what are the main differences? If you recall, and it was very controversial, in Western U.S. We had with Errol bump in the near field for magnitudes about 6 to 7. There is no bump here because there are no data to support or reject it. It makes it more simple. No basin effect. Again, it makes it more simple. And I didn't distinguish between different fault styles. And again, just a reminder, it's based on our publication with my co-author, former co-author, Errol, published in 2007, 2011. Now, I think there is some physics into this model. For example, if you look at PGA, PGA is approximated by a filter, which is shown on the top formula. It is very simple. You can adjust R or attenuation. And it has what I call corner distance in similarity to corner frequency. Basically, the flat area is longer for larger magnitude and smaller for small magnitude. And you can see with, I believe it's red dots, showing that corner distance increase with magnitude. And this part was straightforward brought from Western U.S., basically because there is no constraint for Eastern U.S., and I kind of don't believe that these features can be different, or should be different. Let's say it can be different, of course, but should it be different? I have no clue. This is why I assumed it's same. Now, this is magnitude scaling. Magnitude scaling actually is basically, again, same approximation with different coefficients and with higher scaling than in the West. I will show this later. Attenuation, anelastic attenuation, and not only anelastic. I tried different attenuation slope, and I tried from R-1 to R1.3, and I found out that R-1 fits the best data different distances. Now, I will talk a little bit more about this later. I plugged in Q in this, and this make it adjustable within at least stable continental environment. For example, if we move to, for the beginning, I assume Q equal 1,000, which was in previous publications. It's probably 640, as I heard before yesterday. But basically, if we assume 1,000 for main part of central United States, for Gulf Coast, we probably have to assume 3 times lower Q, which will mean faster attenuation with distance. Now, this is our spectral shape. Now, that's a very critical point, what I want to underscore. What's the difference between conventional models and the model I am advocating is that in this case, I don't have this, whatever you call it, dummy parameter like H, or strange dependence like M square with your attenuations. I don't have this part. But what I and also, as far as I understand, the conventional model assume uncorrelation between different periods because you invert for each period independently, which make you stronger in a way because you can lower standard error adjusting for each period. I cannot do this. I have a shape. As long as I think the shape is correct, and I will show you more, I have to basically invert for the whole shape. This means that whatever you call it, it's a strength and a weakness. The weakness is that clearly in some cases my standard error will be higher. But the strong part is that it is more understandable and explainable from scientific or seismological point of view because, for example, I know that my slope is about omega square, omega minus 2 in most cases. In some cases, I can adjust it. But basically, I have less options for variations. Now, again, I didn't say this, but this spectral shape was developed basically mostly originally on Chichi data, and it is a combination of 2 functions. One is kind of step function or smooth step function, and another is bell type function. Now, just to remind you how I created these shapes, it was, again, based on Chichi data, but in this case I am demonstrating fitting these shapes to Loma Prieta data. And as you can see, in average, this approximation works pretty well. Now, why I'm talking about this a lot? Because basically this same style or the same type of functions can be adjusted, as I believe, to the east. Now, Now I'm showing how it looks for the east. This is my two models. I call it M1 and M2. But basically, they are not much different. It's about 8-9% difference. But they kind of intersect at some distances. But again, you can see the shape, spectral shapes here. They are smooth. There are no whatever bumps or whatever on this. This is how magnitude scaling looks like for a number of frequencies for these two models. Again, I apologize. I will be mixing periods and hertz because, you know, at NRC we operate in frequencies and engineers still like periods. But basically, there are some differences. And again, my first model was based on EPRI 2013, or actually original NGA database. And my second model is more based on the final or latest NGA East database, which was released in September. Okay, now I will show you some tests or correlation between this model and other models. In this case, one of benchmarks for me was SSHAC model. And as you can see, it is different, but in some areas it's very similar. I was trying to preserve the slope as much as I can based on my spectral shapes. And you can see that in some cases amplitude is different. But I'm showing this as an example. Next, it was a bunch of discussions here about how West should be different from East. And from this point of view, I would like to show you a comparison of my Western and Eastern spectral shapes. And what I believe is very important, that at long periods, spectral shapes at the West and the East are more or less similar, which I believe should be for the same magnitudes. And of course, they are significantly different at high frequencies or low periods. Now, I specifically showed this up to 1,000 hertz, because again, this is a model with continuous function. I can go anyway, but basically the idea is that the spectral shape of Eastern US is shifted toward higher frequencies, and it's higher in amplitude. But at longer periods or low frequencies, it's kind of similar. The only thing really I saw here different at magnitude 5. It looks like, according to the data, that at magnitude 5, spectral shape for low frequencies is lower for Eastern US. Honestly, I believe it's an artifact of data processing, nothing else. But since I stay with the data, I have to, at least I believe I have to follow it. That's the basic difference, that at magnitude 5, low frequencies are lower for Eastern US. Now, I did gazillions of tests and comparisons with whatever is available now. And my main benchmark was EPRI 2013 released model. And I plot here all these 4 clusters. And that's what is used now for seismic hazard assessment in the Central Eastern United States. And my 2 models are showing with black and orange dashed lines, and this is for magnitude 5. For magnitude 5, as you can see, I'm slightly on lower end for high frequencies, and if we look at lower frequencies, it's kind of close to the average, which I believe is important for at least consistency reasons. Next couple of slides is for magnitude 7.5. For magnitude 7.5, my model is kind of very close to EPRI model. And same for lower frequencies. Basically, it is kind of, it demonstrates reasonable agreement with what was done before. Now, it was nice of Chris Kramer. He provided me with USGS National Seismic Hazard information about their use of models. Actually, I put the names of the models, but for some of them I don't know what is that. Clearly, the first two or three are very easy to understand. But basically, what this shows that for magnitude 7.6, it is pretty close for what is that? I'm trying to. I didn't put what these frequencies are. It's probably PGA and 10 hertz. That's oh yes, it's written. Sorry, I cannot read even my own plots. Okay, it's higher for 10 hertz than other models in the near field, but it's also maybe a difference because I believe Chris Kramer gave me this for not for rupture distance, but for Joyner-Boer distance. This is why kind of maybe different, slightly different in the near field. But anyway, the fact is it's higher than those NSM HM models at 10 hertz, very close at PGA, and for 5 hertz it's kind of mostly also on probably a higher end, but it's still within the reasonable agreement with existing models, except the two lowest. Okay, now I'm showing comparison with actual data. This is comparison with NJ East September database, and with different lines I show M1 and M2 models, and basically they kind of go in the middle of this data set. Now this is for 2.5 hertz and 0.5 hertz. It's kind of also demonstrate reasonable agreement. Now residuals. Residuals are not as good as I would hope. This is kind of residuals for PGA for 10 hertz. I think in this case it's actually very good, but if you can see, the errors are pretty high. This is one kind of, I don't know, that will be my question to this audience, what to do with standard error. Now, these are residuals for 5 hertz and 2.5 hertz. They are also not too bad. I mean, the model behave, but in the meantime, again, residuals are pretty high. I show you everything in natural logarithm units, but I believe the standard error is pretty high. Now, correction. On this plot, okay, I was hoping to get guidance from NJ East project for site correction, but I didn't get it. This is why kind of I ended up developing my own correction, which is kind of pretty classical. I run SHAC type programs with different profiles, and I got actually, I believe, pretty similar to Norm Abrahamson Silva Kamai model dependence. The only difference, I kind of, in my case, nonlinearity started from about 400 meters per second, but otherwise it was very similar to this. I may end up basically employing your model. But why I had to do it myself, because there is nothing in your model for 2,800 meters per second. That's why. But this plot shows comparison with Atkinson-Burr 06 and Atkinson-Burr 11. As you can see, my correction is closer to Atkinson-Burr 11, but it's kind of in between Atkinson-Burr 11 and Atkinson-Burr 2006. Anyway, that's how correction, VS30 correction was done. Now, coming to the end of this talk, basically what this model can do, or what it's supposed to do, its functional form works reasonably well from magnitude 4 to 9. Of course, I don't suggest to use it to magnitude 9, but I just simply tested that it does behave radically strange. Also, basically, I would say it's tested up to magnitude 7.6, tested on benchmarks. It works up to 2,000 kilometers, but really I paid attention to 1,000 kilometers. Again, why 2,000? Just to make sure that, because in our NRC practice we see that in many cases people want to go beyond 1,000 kilometers. Even they should not do this. This is why kind of I tested that it doesn't behave stupidly or strangely beyond. Period range is from 10 seconds to 100 hertz, and as I mentioned before, since it has a Q parameter, it can be adjusted within stable continental environment for different regions based on Q. What can be potential improvements to this model? I would say, and I was hoping to see this from ground motion simulations, I would like to have at least scaling law between magnitude 5, 6, 7 that they got to make sure that, first stage, to make sure that I'm not doing something crazy. Second, if it's needed, to adjust it based on this. That's my kind of desire for near future. And standard error recommendations, because basically if you just use this data that we have, standard error will be crazy high. That's why I would suggest to go with certain kind of ideas about standard error and plug in into reasonably used models. And the last slide is thanks to Sharon Pizek, Chris Kramer, Scott Stovall, and Dogan Seber, who helped me at different stages or helped me with data or information. Thank you.
Thank you. I do have a question for you.
Sure.
So why do you even consider using the older version of the database, since the reason we reprocessed was to fix the issues with it?
I can tell you why. Because the previous database that EPRI was using is really checked for the different regions and for bad data. Your database, you have many flags. I simply had no time to go through your database and, to get rid of the data which are not useful for me. This is why kind of, if I would have much more time, I probably will, that was my original idea, to use this database. But I use this database almost as is, except I got rid of magnitude lower than 375.
Okay, that's fine. We can talk offline of
yes,
the
basically,
key flags, but the reason we do tremendous amount of work was put in that database to correct errors and issues, and so. I'm
not arguing. This is why I'm showing both results.
Okay.
And again, my answer to you is I was surprised. My original idea was to discard my original model, and basically use only the latest database. But surprisingly, I came up with very similar results. It's 8-9% difference.
No, that's good.
Yeah, but clearly, yes, I would love to clean this database, clean for my purposes of data adjustment, and use it.
It's a good sanity check anyways, so it's good. Okay.
Yes.
Any other questions for
But also, just to add, I think it's good that basically both databases gave more or less similar results, because otherwise we'll be in big trouble if what EPRI did a couple of years ago will be dramatically different. Sorry.
This is Linda. Vladimir, I was wondering, do you have between event and within event residuals? Because I think for the evaluation for the TI team, it may be useful to see such plots. Is this a reasonable request?
It's a reasonable request, but the answer is no.
All right. In the future, are you planning to?
I don't know, because realistically I have some thinking about this specific. We can discuss it. But I'm not sure I can do it in the short time frame.
Yeah, I just had a question about this is Ken Campbell, about your Q term. Is it a function of frequency?
No. And actually I'm still puzzled how you guys doing this, because with frequencies, because as far as I looked recently at all publications, everything is from 1 hertz to 12 hertz. And you extend it to, okay, let's say the answer is no. In my case, Q is Q0 or Q at 1 hertz.
Because
and the reason is because every publications in BSSA I looked at, they go from 1 hertz to 12 hertz. And realistically, at least I don't know how to reasonably extrapolate it to 100 hertz and to longer period. Probably longer periods is fine, but for 100 hertz, I'm not completely, at least I don't understand it.
Yeah, because Q0 is typically at 1 hertz, and so you're sort of ignoring the eta factor. So anyway, I was just curious whether the data, can support a different Q or not as a function of frequency.
The answer, I believe, yes, but I don't know how to do it.
One comment, Vladimir, Gabriel Toro. One advantage of the spectral shape as you're doing it is that in essence you're estimating a lot fewer parameters. So statistically you get more robust numbers. On the other hand, you may be paying a price with the lack of it.
Yes, that's very true. It's very important to understand. Yes, on one side it has advantages because, first of all, it's continuous function. You can go at any periods of frequencies that you want. You can actually check it beyond 10 seconds to make sure it's reasonable. But it is pretty rigid. This is why I clearly most likely cannot achieve standard error, which can be achieved regressing every frequency.
Yeah, I want to go back to a comment that you had made on one of the slides, and I'm not sure if I caught exactly what you meant by this. It was comparing the models, and your comment was for the lower magnitudes at long periods, you had I can't remember exactly how you said it, but you were concerned about the data processing, and maybe this relates to what Christine was talking about.
That's the slide I was talking about. If you look at the left side, you can see 20 kilometers, a slope for magnitude 5 is faster for eastern U.S. than for western U.S. And it's driven by data. And I can say I don't know what is that. But my feeling, it's an artifact of data processing. And artifact either on one side or on other side. Basically, what I'm saying, if you are too conservative and cut off a lot of low frequencies, you will have faster slope. I suspect that it was the case for Eastern database, that Eastern database was maybe too conservative in getting rid of low frequencies, which is, of course, maybe the explanation, of course, I spent 25 years of my career processing data, and I can understand why it can be done, because people are afraid to produce noise. But, okay, you don't have to pay attention to my comment, this comment. This comment was basically made, it's a comparison, and I see basically agreement for 6, 7, and 8, and that's a good sign. When I see difference for magnitude 5, either there are some seismological features that I don't understand, which make East different from West, and
that's fine. I just wanted to make sure that I understood the context of that.
Clearly, I upset somehow Gail.
Yeah, I would interpret that rather differently, because I think that where it's best constrained is at magnitude 5, because that's where the data is, and I don't really see any reason to suspect that there's anything wrong with the data processing. You know, I've also seen in the East, that's just an observation, is that the ground motions at periods of 1 second and longer for the same magnitude tend to be, you know, if anything, a little lower in the East than they are in the West, and I don't find that all that surprising when you consider the difference in crustal structure. I think you have a more gradational profile in the West. I think that there's a tendency for the Western crust to amplify the longer periods to a greater extent, perhaps, than the profile that you have in the East. There may also, in the Western databases, like NGA West, be much more of an influence of basin effects and deep section effects and so on that may not be reflected in the Eastern. And so, to me, when I look at that, what I would find puzzling is why the difference that is seen at magnitude 5 is not there at magnitude 6, 7, and 8.
Okay, I love your explanation because it's more scientific than what I gave. This is why I'm happy to accept it.
Thank you very much. Oh, one more?
I thought from yesterday you were getting similar numbers. So you would have had those two gray curves on top of each other.
Well, they're similar, yeah. But if anything, it's lower. They're similar, but I would say, if anything, you see a slight lowering at longer periods in the East. And if you go out to longer periods than 1 second, if you went to 2 to 3 seconds, then you might see more of a lowering in the East. Potentially. So you don't see this difference between these gray curves, which I agree is where the data are, as being fundamentally inconsistent with what you showed yesterday, or your student showed yesterday? Not to a first approximation, no. You know, because there's just, you're looking at difference for particular distance, like that's one distance. And then by the time you get out to 100 kilometers, I don't know. You'd have to look at that more carefully, but I don't see it being a huge discrepancy.
Okay.
I was trying to match what you were saying yesterday.
Mike.
Okay, I'm just... Thank you, Gail. I was just saying that I was trying to match what you said yesterday in your presentation, that low frequencies in the West and East should be similar, and that's what my belief is also.
Okay, thank you very much. Okay, thank you, Vladimir. So we've got the bigger mic now. So, we're going to switch gears slightly, and our last proponent models is going to be after this talk, after the break. But in the big scheme, big picture that Norm talked about yesterday, we're going to select models based on how they fit on the Salmon's maps and resampled and select from cells. And then we're going to use hanging wall effects models from the west. We haven't decided yet whether it's going to be multiplying or randomly selecting, but Bob Youngs is now going to present a summary of those hanging wall models as we plan to use them for the east.
Good morning. So I'm going to present a proponent hanging wall model that comes from the SWAS project for consideration for use in the NGA East project. So the motivation for this approach, as will be probably discussed a lot more later on this morning, is that we don't have empirical data in the study region to constrain hanging wall effects. We don't really even have it in the NGA West 2 data empirically to well-constrain hanging wall effects. So the concept would be that we would to develop regional models appropriate for the study region based on the data that do not try to address hanging wall effects at all, and that we use on top of these models, we add on a quote better calibrated hanging wall model to address hanging wall effects. And then we take this hanging wall model and apply it to the regional model developed based on the NGA East data, empirical and otherwise. So that's the basic motivation. And so what is meant by better calibrated hanging wall models? So 3 of the NGA West 2 models use numerical simulations to constrain hanging wall effects. They used them, basically there was the same set of simulations available to the teams that chose to do this, and they each used them in slightly different ways. So we have a set of hanging wall factors available from the ASK 2014, CB, and CY 2014 models for a range of magnitudes, basically magnitudes 6.5 to 7.5 were constrained by simulations, and for a range of dips. So we can use those hanging wall factors to develop a hanging wall model, and the basic concept is to fit those predictions with a common form and then represent the uncertainty in that common form with a set of discrete, basically scaled hanging wall backbone curves. And then apply to those scaled hanging wall backbone curves some additional tapers to deal with the distances as you move off of the hanging wall, basically as RJB increases from 0, and for the effect of depth and magnitude on the hanging wall effect. So it turns out, since they all use very similar data, that the data can all be well fit by a common form, and this is the form that I developed to fit those models. It basically is a constant. It scales then with the cosine of dip, which basically treats hanging wall as a geometric factor, and that the width of the envelope or the footprint of the hanging wall is basically scales with the cosine of dip of the fall. So I just apply a lot of the models use dip directly as a variable, but I think cosine dip is a better term to use because of the geometry that it's related to. It has a second factor in here internally that allows for a step function right at the top as you cross into the hanging wall, because all 3 models have basically a step function as you cross from negative RX. I should mention that RX is the dimension that represents the horizontal distance perpendicular to strike measured from the top of the rupture, the projection of the top of the rupture to the surface. Negative RX is in the footwall, positive RX is in the hanging wall. So the hanging wall effect is all modeled as increasing RX as you move into the hanging wall, and all 3 of the models had a small step as you cross from negative RX to positive RX. So this C term setup addresses for that step function and then allows for the increase as you move further back into the hanging wall. The fitted models that were produced by NGA have a small or a relatively weak but magnitude scaling term. In other words, they increase, the hanging wall effect increases slightly with increasing magnitude. And then the various models applied tapers to deal as you move off of the hanging wall. With RAGB increases, they had magnitude tapers and they had depth tapers. As the depth to the top of rupture increases, the hanging wall effect decreases. So we had to address those three aspects. So this is a plot showing the hanging wall factors from the three models, shown by the three colors, and then the fitted common form and its uncertainty band that would be used to represent the distribution of hanging wall, scaled hanging wall backbone curves for sites that are sitting on top of the hanging wall. And you can see that from these that the common form does a good job at representing the trend in all three models and in general capturing the range of the model predictions. So this is a plot of the effect for dips of 20 degrees. These are all four faults that are rupturing to the surface. So this is magnitude 6.5, 7, 7.5, dips of 20, 40, 60, and 80 degrees. So you can see the hanging wall effect dramatically decreasing with increasing dip. So this is basically the model that would represent sites, the hanging wall effect for ruptures that reach the surface and for sites that sit on top of the hanging wall with RJB equal to 0. And you can also see from these why the impact of just using RJB distance will not be capturing the effect that we see from the simulations in dip. In other words, we see dramatic differences between the hanging wall effect for a dip of 20 degrees versus a dip of 80 degrees. And with RJB, both of those sites have RJB of 0, so an RJB model would say that the motion should be the same. The second, attempting to capture the range and predictions, this is the effect of moving off of the hanging wall in the positive Rx direction, basically as RJB increases. Two of the models, the CB14 and CY14, had very similar behaviors shown by the red and sort of yellow curves. And then the ASK model had a relatively simple model to represent that effect. And the basic behavior can be captured with a simple form relating the ratio of the RJB distance to the rupture distance, and it would capture the behavior of the CB and CY models. And the curves here, the dashed curves basically represent as you move off the hanging wall near the top of the rupture in the strike parallel direction, the hanging wall effect attenuates very rapidly. The hanging wall effect attenuates rapidly as you move off in that direction. The solid curves are moving off of the hanging wall, increasing the RJB distance in the RX direction, basically perpendicular to strike, basically further back into the footwall behind the rupture, and there the attenuation of the hanging wall effect is much weaker. So this simple form captures that behavior with a simple geometry. So that is the applied taper for the effect of increasing RJB distance. The effective magnitude for both the ASK and CB14 models applied an assumption that the hanging wall effect goes to 0 as the magnitude decreases from 6.5 to 5.5. And the CY14 model did not apply that, but used a geometric formulation to quantify the hanging wall effect, which basically introduced the magnitude term, because as magnitudes get smaller, the rupture width gets smaller, and therefore the hanging wall effect gets smaller. But there was no specific magnitude taper, as in the case of CB14 and ASK14, just assumed that by the time you got to 5.5, there was no hanging wall effect. Some simulations that were conducted at smaller magnitudes that were conducted in support of the SWAS project showed that even at magnitudes below 6.5 and down to magnitudes 5.5 and 6, there were significant hanging wall effects. So the proponent model is that we do not apply the ASK and 14 filters. Basically, we just used an extrapolation of the hanging wall effects predicted at larger magnitudes down to smaller magnitudes. And basically, so that sets that taper term T2 basically equal to 1 at all magnitudes. The third is a depth term, and there all of the models had quite different behaviors, but basically an indication that the hanging wall effect decreased as the rupture got deeper. In other words, as you go to large depths, then where the entire rupture is, the top of rupture is down by about 12 kilometers, then the hanging wall effects attenuated to very low amplitudes, so very simple linear depth term taper is established to sort of average the effect for the three models. So that's the basic form of the hanging wall model, and then I don't know if these are going to show very well. These are comparisons of the predictions. So the hanging wall models were all developed based on one set of simulations that were done by Graves and Protarca in support of NGA West, the project, NGA West 2 project. And then subsequent to that, all three methods brought the finite fault simulation methods that have passed the SSHAC validation, the Graves Protarca, the San Diego State, and the XSIM model, which are now all being implemented on the platform, were used to perform simulations for hanging wall effects for a range of magnitudes and dips. These were the simulations that indicated in part that the hanging wall effect still is present at smaller magnitudes. And these plots show the comparison of the hanging wall effects from those three models, which are colored symbols, with the predictions of the simple model based on the NGA West 2 models for a range of magnitudes 5.5 for different depths, 0, 2.5, 7, and 12. Again, for magnitude 6 for depths of 2.5, 7, and 12. And then for a range of 6.5 for depths of 0 and 7. And for magnitude 7 for for a range of dips. So basically the model is capturing the behavior of all three sets of simulations. And this plot here just shows the range of the scaled backbone hanging wall models compared with the simulations for magnitude 6.5 at different dips and depths. So that's the proponent model for hanging wall effects. Any questions?
No. So most of the TI team has seen this before, so this is the model that we've evaluated as part of SWIS. I think the question is if there's other people who have questions in terms of how we're putting these all together.
Emrah Yener. I was wondering how the change in fault dimension or rupture dimensions when you switch from Western to Eastern North America due to increase in static stress drop will affect this hanging wall effect model.
So it would enter through the width. So basically, the hanging wall model is a geometric model.
Right.
And so basically, if you're on top of the rupture, then you'll have the same, the width will be narrower.
Right.
So it enters through the size of the rupture.
Okay, thank you.
But it's still just a multiplicative term that applies to the overall scaling of the model. This is just a term that's added on top of the overall scaling that's coming from other sources.
Thank you.
Vladimir Grazer. Maybe I just missed this. Is this effect, hanging wall effect, frequency dependent, or it's kind of...
It's frequency dependent. It decays as you get to longer periods, based on the models, the simulation models that were developed as a part of it. It is frequency dependent.
Okay.
I'm showing PGA, but it decays as you get to long periods.
Okay. And is there any documentation, I just want to look, or whatever, presentations which describe this in more detail?
Yes, is the answer. There's a appendix in the Swiss report that we can make available to everybody.
Yes, please. Thank you.
Gabriel Toro, and this may not be a fair question, but I was just wondering about the hazard significance of the hanging wall effect in the east for typical 5.5 and 6.5, and where the hanging wall effect is more or less important than, say, directivity. Based on, for example, some of what was presented yesterday, there was some talk about, again, much higher motions when the rupture was propagated towards you for the reverse events and so on. Has the TI team given any thought to those issues?
Yes. Is this for
Well, I would say yes, in the sense that the TI team is not planning to spend days and days and days agonizing about hanging wall effects. It's probably planning to adopt a relatively simple model that can be applied and then go forward.
That's good. What about directivity? What about directivity? Is that, is it in the cards? Should it be in the cards?
You can answer that one. That's off topic.
This was never a part of the scope of NGEs. Okay. Even the hanging wall is added scope. It was never our intent to address. Yeah,
which is a fair answer.
Yeah, it's all going to go in the sigma because we don't have information first, and then
And we have very few cases where we have well-defined fault planes that we can assign, where we can make some assessment about whether the site would be affected by directivity, other than that it's a lot of random orientations. So a lot of that would just get washed out in the randomness of what the ruptures are going to be.
Yep. Do you want to?
It's easier to let's say, accommodate directivity in the standard deviation, but on the hanging wall effect, if we don't use it, we have to consider the bias in the median predictions close in. So that's a bigger issue on the impacts on the hazard. So it just comes into the dealing with the local host zone, right, and how you're going to model the aerial sources, and if you fill it with virtual faults, you will get a different answer in the mean from incorporating virtual faults with hanging wall effects and incorporating virtual faults without hanging wall effects. That's really the key reason we're sticking it in there.
So next,
John?
So I guess I have two questions. The first is, as far as I can remember, all the proponent GMPs are using rupture distance, right? Nobody's using RJB. Is that right? Correct?
It's not true, but the current models under development, we encourage them to use RUP, but the EPRI models are
RJB.
JB. Yes.
Okay, so there is some RJB.
Yes, I mean, right. So that effect can be captured. The basic scaling from those and distance scaling can be captured for sites off the hanging wall, and not worrying about that. Not trying to address hanging wall effects with them.
So if there are some models using RJB, then you have the same situation in the West where some models are accounting for the hanging wall through RJB, and then models that use RREP have to have this effect added on.
So, for instance, in the SWUS project, we used the RJB models and the RREP models to develop a footwall model, and then added the hanging wall term to it.
But only to the RREP.
To the final set of models that are all RREP. And we did, for instance, one case, we did use RJB models. RJB probably works reasonably well if the dips are staying in a relatively narrow range. You know, about around 45 degrees, they have similar behavior. It just does not capture the range and hanging wall effects we see from simulations over a wide range of dips.
Right, and so that leads
and
to
depth.
Right, and that leads to my second question, which is on the next slide, I think. Okay, so this is showing the hanging wall effects with Rx as you go off the fault for the different magnitudes, right?
Oh, yes. You're still on top of the fault.
Some portion of this is on the fault, and some portion.
All of this is on top of the fault.
All of it's on the fault. I see.
Okay. This is all RJB zero distance.
Okay. So I'm just trying to. If you did this, these are for different dip angles, right?
Yeah.
20 and 40. So if you were to add to these plots the implied hanging wall effect by using RJB, has that been done?
Yes, it behaves completely differently.
Even for the 40 degrees?
Yes, I mean, dip is irrelevant for RJB. If you're at Rx 0 to 10, if RJB is still 0, the ground motion is the same.
It would be flat across the space, is what you're saying.
Yeah.
This is the adjustment to the distance. So when you're at a higher Rx, your RREP will also be higher, right? Because you're further away from the fault. So this is the amount that's added in. So you have to take this plus the slope of the attenuation to get back to the total. I think
you have to create an approximation of a hanging wall effect for RJB. You have to decide what distance ratio are you going to use to calculate that.
Yeah.
So that makes it difficult first to quantify what is the hanging wall effect for RJB is 0. I mean, for the RJB model.
It's just, we just leave it in. The RJB model leaves it in, right? I mean, it implicitly incorporates the hanging wall effect based on the distance metric definition. I do think what John is getting at is at 45 degrees, these things are comparable in terms of their net effect. But as you go to steeper or flatter dips, then they really diverge tremendously.
Right, and so I'm having trouble thinking of just how to do it with plots formatted this way, but it would be nice to see, maybe with a different set of plots, how your model is very different from what you would get from RJB. I mean, I've made some plots like that, and it's using a different horizontal axis, I guess, but I get something that looks very close at, like you say, around 45 degrees dip.
The 45, I think the effects between the two models are quite the same if you're using RJB. It's when you get to 20 degrees.
Right. And that's where we don't have data, right? So there's no data to support these strong effects of dip. So that's really where the simulations are important.
Well, the simulations are really controlling. The simulations show that dip is a big factor on hanging wall effect and depth. And for instance, the same with RJB. If the rupture is down or at the surface, it's the same ground motion.
But we do have data at 30 degrees from Chi-Chi, which is a really important data set. And that's quite different from 45. And that's where you can see the RJB metric really isn't picking up the scaling that we observed from Chi-Chi. That's one of the reasons why those models are so different for that particular earthquake.
Art?
I think I know the answer to this question, but have you thought about using different distance metrics like our root mean squared distance or something, average over the fault plane? I mean, that's essentially what this is capturing, isn't it?
Yes. Well, I can say that Brian, where is Brian here today? There he is. Brian did some work a long time ago, in which he showed that RMS works very well in capturing hanging wall effects. And so if you use RMS distance, the trouble with RMS distance is that it's computationally expensive and hazard. But you could, in fact, if you switch to RMS, that may do a very good job of capturing hanging wall effects. And then, also the problem, I think, with RMS is if you have a 300-kilometer long fault, how do you do the RMS over that 300-kilometer long? You have to decide, is there some distance range you computed over to do the ground motions? 300-kilometer versus a 600-kilometer long fault are going to have different RMS distances if you use the whole fault, but are the ground motions really going to be that different for those at the same distance down near the end? So it works well for smaller faults and hanging wall effects, but when you get to big, long ruptures, then it has issue about how much for the fault do you RMS over. So
you probably want to use the RMS 1 over R.
You have to, yeah.
But then the hazard calculation will take forever.
Yes. So, but Robin doesn't care.
He doesn't.
Okay, thank you. So I would be in favor in starting the break a bit early because the other talks are pretty tight and packed, and I'm sure there's going to be a lot of questions. So thank you, Bob, and let's come back at 10:05. So enjoy the coffee in the back. And we need, Jeff, we need your presentation, Nico, and Justin. Thank you.
You sent it by email to Christine, right?
Yeah, I have it. You're going first, right? Okay, thanks.
share that stuff. How do you full view? Okay, let me. Okay, people, we're going to start again. I gave you an extra 5 minutes, so. Okay, John E. Bell. Okay, group, we're starting in 5 seconds. 5, 4, 3, 2, 1. Okay. Okay. Yes, thank you, everyone. So the next set of presentations are for the pure FAS to RVT to PSA model. And the reason we have more time is that I prepared the agenda. No, that's not true. The reason we have more time is there's a lot of topics to cover because it's really a new approach that is used for ground motion modeling. And we're going to break that down into topics. There are things we never showed the PPRP or even the different participants here. So the first topic is going to be how we're going to use the RVT approach and decisions that were made from the RVT working group that was set up to deal with issues in RVT. Okay, that's random vibration theory. Then I'm going to do a quick switcheroo in the order of the presentations you have here. The next presentation is going to be on the magnitude scaling from the finite fault simulations using the SSHAC broadband platform. And after that, we'll have the presentation of the regression by Justin Hollenbach on regression on data in FAS space. And then we will conclude with the last presentation, which is the other part that is required for RVT, for amplitude spectrum and duration. So the last part is the duration, and Nico Kuhn is going to do the presentation on duration, then shows how when you take the model from Justin with the extrapolation in magnitude, with the duration model, how you eventually get the PSA model. Okay? So that's going through all this. So our first presentation is by Albert, who's going to present the conclusions of the RVT working group.
Thank you, Christine, and good morning. Again, I'm Albert Kotke, and I'm presenting this work that has been done by a number of collaborators, including Norm Abrahamson, Dave Bohr, Christine Glay, Justin Hollenbach, Tadahiro Kishida, Arminder Kriegen, Nico Kuhn, Ellen Raschi, Walt Silva, Eric Thompson, and Xiaowei Wang. And again, the topic is the Pacific Earthquake Engineering Research Approach to Random Vibration Theory for the NGA East project. Just a brief outline of the talk today. First, I want to go over just a brief introduction to the motivation for using RVT for ground motion models. Introduce what RVT, or random vibration theory, is. Discuss the peak factor formulations, specifically the Van Mark peak distribution, and some discussion of why we selected this as the preferred peak factor. Next, I want to talk about processing time series for use in evaluating or developing an RVT-based ground motion model. Look at the effective amplitude, which is our definition of amplitude that we're going to be developing the motion for, and look at time series processing to maintain characteristics for the RVT motion, and wrap everything up in a conclusion. First of all, why do we want to look at RVT? The response spectrum really has been the standard for ground motion models, and this is primarily because of the strong applicability of the response spectrum in engineering design and evaluation. The response spectrum simplifies ground motions and depends on the characteristics of the single degree of freedom oscillators. Specifically, or I guess the major disadvantage of this is that the response at a specific natural frequency or natural period depends on the response at lower frequencies or longer periods. With the Fourier amplitude spectra, it simplifies this problem, and this is especially important for application of factors, and these factors could include kappa, or as I like to call it, site attenuation, or site amplification, which have been previously dependent on the spectral shape. So different magnitudes or differences would have different kappa scalings or site amplification scalings. Also, the Fourier amplitude spectra allows us to use the limited bandwidth of recorded motions that we have available. However, by using the Fourier amplitude spectra, we no longer have that direct engineering application, so we need to look at RVT as a method for transforming our Fourier amplitude spectra into response spectra, and RVT allows us to do this. So what is RVT? RVT, random vibration theory, defines a motion using two parameters, really. First is the frequency content. The frequency content is defined usually using a Fourier amplitude spectrum in the seismological community. Structural engineers use a power spectral density function, or it can be indirectly specified using a response spectrum. Although specifying the response spectrum, the high frequency characterization isn't as strong. The second portion is the stationary duration, and this is the time over which the statistical properties of the motion are constant. Expected values in the time domain are then computed using extreme value statistics, which are used to define the peak factor relationship. The response of a system, such as a site response, oscillator response, or structural response, can then be computed by applying the appropriate transfer function. And so most of these transfer functions for developing a ground motion are the single degree of freedom transfer function. And we'll just go through the steps of an RVT calculation. If we have the frequency content, the Fourier amplitude spectrum, the first thing we do is we apply a transfer function. If we want to calculate the response at a specific, say, oscillator frequency, or if we're just looking for the peak ground acceleration, we don't need to apply this transfer function. The next step is to compute the root mean squared response, which is simply the zeroth moment divided by the duration of the ground motion until we take the square root of that. So this is the first time we have what's called the spectral moment, m sub 0 there. And this is one of the major characteristics or major ways we define characteristics of the motions for RVT. And we'll use a number of different spectral moments, 0, 1, 2, and 4 are typically used. Once we have the root mean squared response, YRMS, we can compute the peak factor using equations that I'll get to in a moment. And then we can compute the peak time domain value by applying the peak factor to the root mean squared response. So what are some peak factor formulations? And what do they do? First, peak factor formulations define the distributions of peaks based off of spectral moments of the ground motion. There are a number of peak factor formulations that have been proposed and have been used. One of the earliest is Cartwright and Lungman-Higgins. This has been used by Dave Bohr's SM-SIM after some modifications to it. It was simplified by Davenport in 1964 to an asymptotic solution. Van Mark took this and improved its ability to capture clustering the time domain. Van Mark's solution was then simplified into an asymptotic solution by Dierkriegen in 83, and the Dierkriegen formulation was slightly modified by Toro and McGuire in 87. In general, RVT assumes band-limited white Gaussian noise with a zero mean, and stationary stochastic processes over a duration interval. That means the statistics of the ground motion aren't changing. And finally, random phase. The Cartwright and Lungman-Higgins model assumes statistical independence of peaks, a Poisson process, which is a significant limitation for narrowband processes. Van Mark 76 addressed this limitation to include the potential for temporal clustering. So this is the Van Mark 1975 peak distribution. It defines a cumulative distribution of peak values defined by this equation. And so we can see here the really input of the ground motions are n sub z, which is the number of zero crossings, again based off of the spectral moments, and what he's calling the effective bandwidth, which is again based off of the ratio of spectral moments. So I guess the reason to show this equation is to understand the importance or the simplified characterization of the ground motion just based off of the spectral moments. And from this distribution of peak values, we can then compute the expected peak factor using the relationship below. One of the alternatives we considered was the Deer-Cregan 1983 peak factors, and this is a figure that Ellen Rasky put together showing the difference between the DK83 and the Van Mark 75. And what we see is that at small numbers of zero crossings, the simplification by Deer-Cregan results in some minor differences between the peak factors computed by these two methods. And therefore, we selected the Van Mark complete equation because of the ability to capture this behavior at low numbers of zero crossings. And the low numbers of zero crossings are important at long period, low frequency, where you don't see many zero crossings of the oscillator. Using RVT beyond just response spectrum calculations is something that we also wanted to consider. Some work done by myself and Ellen Rasky concluded that there were some differences between time series and RVT site response analysis. Some ongoing work has shown that by using the Deer-Cregan peak factors and subsequently the Van Mark peak factors, we can improve the ability for time series and RVT site response because of the effect of spatial or temporal clustering of the peaks. So some just brief discussion of the peak factors. The Cartwright and Lagun-Higgins assume statistical independence between local peaks, which is a significant approximation. The shortcoming can be partially addressed through empirical duration modification, such as that done by Dave Bohr and Eric Thompson in 2012, and also and even going back as far as Bohr and Joyner in 1984. However, this duration modification really only works for the correction that it's being worked for. So the Bohr and Thompson is developing a duration correction for response spectra. If you apply it beyond, such as with site response, you may get errors because it's not addressing the underlying statistical deficiencies of the method. The Van Mark 75 is more theoretically robust, but it's not as widely used within seismology. However, SMSIM, I believe, has now been updated to include it. We're going to be developing empirical duration modifications for Van Mark so that we are getting good agreement or ensuring good agreement with simulated time series. The Cartwright and Lagun-Higgins 1956 and Van Mark 75 are both recommended, but the Van Mark 75 is the preferred peak factor formulation. All right, moving on from peak factors, now I want to talk a little bit about the time series for RVT. We have Fourier amplitude spectra computed from time series, and these are going to be used to develop the ground motion model of the Fourier amplitude spectrum. We need to develop an orientation-independent definition of the Fourier amplitude spectrum to represent two horizontal components from as-recorded ground motions. And the second is to reduce the frequency spacing to a reasonable number while maintaining consistent characteristics for RVT peak factor calculations. So the first is how do we characterize the motion, and we're simply going to be averaging on the squared Fourier amplitude spectrum to maintain power of the ground motion. So here we take the horizontal 1 and horizontal 2 components, square them independently, take the average, and then take the square root. And this is what we're defining as the effective amplitude. Okay, now let's talk about time series characteristics. The time series in the NGA database can be broken up into two types, depending on sampling rate and time steps. And you can see the characteristics of the two types here. From these two types, we extend them out using zero padding to long durations, something like 60 minutes long, which are quite long. So we then want to reduce that back down into what this provides is a consistent frequency step across all motions. And so you can see we actually end up with two frequency steps. What we then want to do is reduce the frequency step back down to something that's a little more reasonable. But we also want to make sure that we maintain characteristics of the RVT characteristics of the motion through this simplification. So we looked at a number of different filtering methods or smoothing methods, and Kono Onomachi 1988 was the selected as the preferred smoothing window. We looked at a number of different characteristics, the zeroth moment, the bandwidth parameter there, the frequencies of zero crossings and the frequencies of extrema, again based off of the spectral moments. And we considered how many points per decade in frequency space do we need to define the motion, and what is the width of the smoothing operator that should be applied. So this is some work that Justin Hollenbach worked on. On the last two columns, we have the points per decade and operator width. And you can see if we're using 100 frequency points per decade with the smoothing operator of 1/30th of a decade, we maintain a 1% agreement between pre-smoothing and post-smoothing for nearly all motions. And so these are the characteristics of the smoothed Fourier amplitude spectra or effective amplitude spectra that are selected for use. As an example, we have the green line is the smoothed effective amplitude spectra, and the black is the unprocessed amplitude spectra, and the red lines indicate the high-pass and low-pass filters. So in conclusion, a range of peak factor formulations were considered by our working group for response spectrum calculations, but also in applications beyond that in structural and site response. The Vanmark 75 is the preferred RVT peak factor formulation due to its ability to model both the response spectra as well as other responses. The effective amplitude spectra will be computed by the average power of the two horizontal components. We examined the standard time series processing methodology and evaluated this against RVT parameters. The recommended processing approach is the Kono Onomachi 98 operator with a width of 1/30th of a decade and 100 frequency points per decade. With that, I'd like to thank you for your attention and ask if there are any questions.
Thank you, Albert. We were actually just discussing this. So I want to invite questions, comments. Yes, I knew you would ask. Oh, you have one. Go ahead, please.
Dedicated. One question, Albert, of clarification. We can talk more about this later. When you in the Vanmark procedure, the way you are applying it, how are you accounting for the non-stationarity? Because again, the Vanmark procedure accounts mainly with bandwidth, right? And you, instead of using all the peaks, you use a smaller number of peaks, essentially. Are you accounting for the non-stationarity using something like the Bohren-Joyner or Bohren-Thompson extended durations? Okay, because there's another formulation of that we have in the 87 paper, which has a non-stationarity factor on the RMS.
Right. And so Eric and Dave have developed or are working on developing a stationarity factor using it the same approach that they developed in 2012 for the Cartwright and Lugano-Higgins peak factors.
Okay, because I think the other one is a little bit more physical, the one we have in the 87 paper. Have you tried it?
I have not made the comparison between your stationarity factor and Dave's, but that would be a good test.
Okay.
Dave?
Yeah, actually, Eric and I have finished the new adjustment coefficients, but we've done it for, actually I'm a little confused. We did it for the Vanmark Dirk-Harrigian 1980. I'm not familiar with the Dirk-Harrigian 1983.
Yeah, 80 I think is a better reference.
It's equation 2, right?
It's equation 2 in 1980. That's what we did. So do we have to redo it now? Is there something different? Oh,
no, I think
you.
I gave him the 83, and that's up my memory as a reference.
There's like 3 different Dirk-Harrigian references, and I picked.
Okay.
I used 83, but they're the same.
You definitely have to make an adjustment. You can't just use the RVT without doing that. You know, the non-stationarity is a very important factor.
So that was good.
Does that answer your question, Gabe, or would you like more of a formal study of it?
It does, certainly.
And the RVT report is in preparation to be shared. Yes.
I was asking Christine, can you go to your table where you pick the smoothing that you're getting, that one? So
this is at 2 seconds, just for what it's worth.
Right, but what I was asking her is that there's a whole probably range of different combinations of points per decade in operator that would also have given you a similar fit, right? Because this now looks, when you see this, you think this is the magic combination. But if I had done 50 points per decade and 1 over 10 or 15, it would be about the same. Is that right?
Justin's nodding his head yes.
Okay.
But it does fall off.
We wanted to keep a number of points that was also reasonable, 100 points per decade. That gives us about 300 points to work with. It's a compromise. There's a choice, right, made there as well. So, yes. Justin, do you want to add something? Do you want to? Man, this is fun. Okay, thank you very much. Thank you, Albert, for your presentation. So the next speaker is going to be Jeff Bayless. Do you need me to?
Yeah. Thanks, Christine. Hi, everyone. I'm Jeff Bayless. I'm going to be talking about the finite fault simulations that were performed using the SSHAC broadband platform as an aid in developing this empirical FAS model. And this is work done by myself and Christine. So a little bit of background. A conclusion from the NJE SSHAC workshop in July was that the finite fault simulations, as implemented on the broadband platform, were not mature enough to use for predicting absolute values. Instead, the recommendation was only their relative scaling should be used. So as a result, we performed simulations with the latest version of the platform for a set of forward scenarios in order to assess how the simulations scale with magnitude in Fourier amplitude space and PSA space. And the results of these simulations are implemented in the empirical model, which is going to be the next talk by Justin. And the scaling in the PSA will also be shared with the GMP developers, as well as the FAS scaling. So a little bit about the platform and the version that we used. I'm calling it version 14.10 because I don't know if that's actually official, but it's pretty much the latest version that we have, including all the most recent updates the modelers provided for the eastern United States. We used 4 simulation methods. They're listed here. In the following slides, I'll use these nicknames: GP for Graves and Patarca, SD for San Diego, EX for XSIM, and SB for Santa Barbara. And then the people associated with those methods are listed. The velocity model for all the simulations was selected as the Mineral Virginia one, with a top velocity of 1 kilometer per second. And then for each simulation we did, we used 16 source realizations, with each one having a random hypocenter placement and a different source. And that random hypocenter was placed a reasonable distance away from the fault edge. So the scenario events, all of them that we looked at were reverse, with strike 0, dip 45, and average rake of 90 degrees. We looked at 5 magnitudes, ranging from 5 to 8. And for each magnitude, we looked at 3 depths to top of rupture cases. So 0 kilometers, 5 kilometers, and 10, with the exception being we didn't use Z Tor equals 10 for the largest magnitude, 8, because it was getting too deep. And here are the fault dimensions, which were determined using the stable continental region relationships of Leonard 2010. In the parentheses are the actual values calculated with that relation, and then the bold ones not in the parentheses are the rounded values. So the magnitude 5 is 2.5 by 2.5 kilometers, and then the biggest one, the magnitude 8, is 160 kilometers long and 40 kilometers width. That's down dip width. And this is just a table. I'll go over it quickly, but it lists the 14 event scenarios that we have and the parameters that are used in the platform source description files. So you basically just need to give a magnitude, strike, rake, dip, Z-tor, which goes from 0, 5 to 10, and then the dimensions. Okay, and the setup of the stations for these scenarios. For each one, we set up stations around the fault in constant rupture distance rings. So I'll show a figure on the next slide to make that more clear. But all the stations were on the footwall side, and we had a total of 10 stations in each RRUP ring, and these are equally spaced within that ring. So our R rupture distances, there's 12 of them. They're 5, 10, 15, all the way up to 100 kilometers, with the exception no 5 kilometers for the Z-tor equals 10 scenario, because that's impossible. And then just a small aside, there's over 200,000 simulated time series with this combination of stations, events, methods, so on. So there's a lot. Okay, this is a map of an example station setup. The red, the fault plane is shown in red, a little bit transparent, with the top edge is solid, and then the dots surrounding it are the station layouts. They're color-coded by rupture distance, and the little legend up here says which one is which, distance-wise. So all the way out here, the brown is 100 kilometers. And this is for the 6.5 reverse case with Z-tor of 0 kilometers. And then I'm going to flip to the next one, and it's the Z-tor of 5 kilometers, so the fault is just a little bit deeper. And then you can see that the station setup has changed slightly because for example, the 5 kilometer RRUP ring is now right on top of the fault. And then a third example, just to give you an idea of how these change, this is the magnitude 8 for Z-tor of 0. So that's what the station setup looked like, and that's what the events were. Now jumping all the way to the processing of the results. This is the procedure that we followed to reduce the huge amount of information that we gathered from the simulations down to a manageable amount that we could use in the empirical models. So the first step was, for each of those 200,000 something simulated time series, we computed the FAS, and this was using Dave's TSPP package. And then for these following steps are for a given scenario with a Z-tor and a simulation method, for example, Graves and Pitarka or XSIM. First, we calculate the geometric mean of the Fourier amplitude spectra at each station over the 16 source realizations. So those are the different realizations of hypocenters. And that gives us like one value, or one FAS at that station over the realizations. I call this FAS sub I. And then we take the geometric mean of this FAS sub I at each of the RRUP bands. So in essence, we're averaging over that constant rupture distance band to further reduce the problem. And I call this FAS sub J. And you get 12 of these because there's 12 rupture distances, which are listed here. And then this FAS sub J is smoothed using Kono and Amachi with the smoothing parameter B, that B equals 30 that Albert was just showing. And this is repeated for magnitudes 5, 5.5, 6.5, 7.5, and 8. Then we calculate the ratios in FAS space and PSA space using ROT-D50 relative to the magnitude 5 scenario. So for example, for the 5.5, we take the ratio of the FAS from the 5.5 to the FAS from the magnitude 5. And the same thing with the PSA. Do that for all the magnitudes. And this is our, relative increase. And then I would repeat steps 2 through 6 for each of the different cases of depth to top of rupture and for each simulation method. So hopefully everyone followed all that, and then you can understand the next plots. So one of the products that we have are ROT-D50 spectra for each RUP ring, and this is plotted with existing GMPEs sort of as a sanity check. So I'll kind of go through this quickly because this is not something that's used in the model itself, but more of something along the way. But the red dots or the red squares with the blue boxes are the simulations, and the purple and green dots are the GMPEs. So you can just kind of see with this is spectral acceleration versus period, the fit is okay. The next set of products are number 2, Fourier amplitude spectra and ROT-D50 spectra of individual stations, which are also plotted as sort of a sanity check to make sure things are going well. And these are averaged and smooth. And then those ratios that I was talking about relative to the magnitude 5.0 case. And these are plotted as FAS ratio versus frequency first. Okay, so the next slide is going to be kind of busy. But it's for the Z-Tor equals 5, RUP equals 20 ring, and for varying magnitude and frequency. All right, everything on the left side is for FAS. Everything on the right side is for PSA, ROT-D50. The top shows for the 5 different magnitudes, each of the individual FAS sub J. So it's the Fourier amplitude spectrum of the individual R rupture ring. Those are in gray. They're kind of hard to see because they overlap and there's a lot of, wiggles. But this is for XSIM, as you can see in the middle. Of course, the lowest is magnitude 5 and then going up to magnitude 8. This is the top left plot. The blue line, which you can't really see that well, is the geometric mean of those RUP FAS sub J. So this is, again, for R rupture equals 20 kilometers. And then the green line is the smooth version of that geometric mean, which is really not that different. Okay. The lower left, again, this is FAS, and it's versus frequency. These are the ratios relative to the magnitude 5. So the black line is the ratio of magnitude 5 to magnitude 5. It's 1. And then going up, blue, orange, green, purple, increasing magnitude. And on the right side is the same exact thing except with ROT-D50. The individual stations are lighter, and then the average geometric mean is dark blue. So this is XSIM. This is Graves and Pitarka. And as you can see, there's a little bit of a dip at around 1 second or 1 hertz. Otherwise, these FAS ratios are quite similar to XSIM, with the exception of that dip, and then at very low frequencies. So I'll let this soak in for a second. There is some chatter. If anyone has a question, I don't mind answering right now. Yeah.
We may as well share our sidebar. I was just asking Rob what that dip was about, whether it was a notch filter thing, and he was saying, no, it's a surface wave effect, and then he was going to say...
Exactly. it is a little bit peculiar, but so what's happening is we're doing the simulations in a 1D velocity structure that's fairly hard rock. And as you get up to the larger magnitudes, even though our station is only 20 kilometers away, there are parts of the fault that are contributing that are further away. And in this velocity structure, the surface waves tend to be large out at 3 to 6 seconds. And there's also kind of a deficiency of energy around 1 to 2 seconds. So there's that's what there's a dip there, and then there's kind of a bump out. I guess this is in frequency, a little bit to the left. Now, I did some tests where I replaced that velocity structure with a Northern California rock structure, and it basically fills in that kind of wiggle. And so that's primarily what I'm using to base the interpretation that that's due to the velocity structure and the way that the surface waves are building up.
Okay. And the next is San Diego State University, where you see there's some funkiness going on around 1 second again, and the magnitude 8 actually crosses below the magnitude 7.5. And then the same thing for UC Santa Barbara. Don't shoot the messenger. Okay, this figure is a compilation of the ratios, again relative to the magnitude 5, but this time just for the magnitude 7.5 simulations and for the 4 methods on one plot. So you can see the legend black is Graves and Pitarka, so on and so forth, just to compare the methods. Okay, the next product is, again, this ratio plotted versus magnitude. So here are, again, the 4 different methods, and this is for 0.1 hertz, the ratio on the y-axis, and the magnitude on the x-axis. So increasing magnitude, sort of what you'd expect here. And the same thing for 0.2 hertz, 0.5 hertz. I think the black is right along with the blue in this one. And then 1.0 hertz. Okay, the next thing I'm going to show is a fit using these ratio versus magnitude plots using the functional form shown here. And this is to obtain the frequency and distance dependent coefficients B2 and C2. So there's a linear and a magnitude squared term here. That'll be a little clearer with this. So the black lines are the Graves and Pitarka scaling at frequencies ranging from 0.5 to 20 hertz. And then the green lines are a fit of each of them using this functional form. And so it turns out for the Z-Tour of 5 kilometer and our RUP of 20 kilometer case, B2 and C2 look like this, where once again Graves and Pitarka is the black and so on and so forth. And the mean here is purple. And so these are the parameters that are going to go into the empirical model, B2 and C2, which are frequency dependent and distance dependent. And in this case, so far, the coefficients have been selected from the Graves and Petarca model using the top of rupture 5-kilometer case. Future work will be to smooth this model over distances and Z-tours, and also a similar approach will be used for the spectral acceleration ratios. And that's all I have. I wanted to thank the people listed here.
Okay, questions for Jeff? Art. Gabe, you still have our mic? One? Yes, good. Okay.
This is Art Franco, USGS. This isn't meant to attack you, Jeff, but I think this whole approach of using the Fourier amplitude spectra and scaling them and then using the result to get your response spectra, I think that's very, very wrong. And you're losing all this information about the phasing and the synthetic seismograms by going to the Fourier amplitude spectrum. And in the end, you want to do the response spectrum. So the best way to have done this was to calibrate the synthetics, the finite fault procedure with the Fourier spectra and making sure they fit that. And then using these finite fault simulations for the larger magnitudes. Problem is, 2 of the methods are behaving badly, and they're not scaling things properly. One problem is the simulations weren't done to a large enough distance. You need to get several fault dimensions away so you can test the scaling of these different methods, and 100 kilometers is not going to do it. But obviously, 2 of the models are not scaling properly, and they should just be discarded at this point. And I think we can have confidence in the absolute values of some of these finite fault simulations, like the Graves and Petarca and the XSIM, and we should use that. And the scaling of the Fourier amplitude spectra, you lose all this information that you have in the synthetic seismograms, and then you're assuming random vibration theory and all the stochastic stationarity of the waveforms, which is just not true. And so I don't think this is conceptually correct.
So Art and I had multiple discussions on that in the past. Quick, I guess, okay, acknowledge, check mark. One thing is that we're also doing PSA modeling, and we're doing these ratios in PSA. We can check and make sure this is not introducing a bias. Our intent of using the finite fault simulations was really to focus more on the low frequencies first and closer distances, because our idea was really to constrain the lower part of the spectrum. So we're computing both in FAS and PSA, so hopefully we can do that check at the end, make sure it's done right. And we'll look at the Salmons maps later, and even if we have not had compelling proof or evidence that the methods really worked well for their absolute values, but what we can do, and we've discussed talking, is using the absolute value still as the background of Salmons maps as a check, and we'll have to see. We may think of other ways we can use them as well. So.
Well, it just seems to me like you're losing the science in all this processes. You're basically trying to come up with a pragmatic solution to solving your problem, which is fine. But, in all these kind of steps, you're losing the science, or you're not trusting the science.
The part then, okay, then a question for you. We have a couple issues in the East. One of them is that more than 80% of that database, it's actually more, 90% when we look at the events we can actually use, is from the T array. We stop at 15 hertz. How can we go with PSA beyond that? That's one thing. So we need that. The kappa adjustments are really difficult in PSA space. So that's why this approach was really selected, to try to solve those issues. Again, this is not the only model. We have a suite of models, right? And this is only one of them that's there. So
Well, you treat that like we've always treated that. We've had models of kappa, we've had models of Q and all that, and we put that into our simulations. So, and then we calculate the time series and we calculate the response spectrum from that. So that's always how it's been working. You know, the stuff that Gal's been doing for 20 years is based on that procedure. And I think that's a logical way of doing things. It honors the Fourier amplitude spectra and gives you a forward model. That's science. You have your data, you have your parameters that you get from looking at small earthquakes, and you have your source models, and you scale it up. That's what
we're also
has been
doing
done.
that. It's not, we're not rejecting this. We're also doing that. So.
Well, I think that this doesn't add anything to the situation, and I think it can very well subtract the situation.
Christian? No, I will. Let me say why we're going this way, and I think this is going to. I think you're going to see more of this in the next 5 years, not less. And the reason is by building our model on Fourier amplitude spectra to start with, actually gives us an easier way to deal with the seismology science side and bringing that in terms of how spectra scale as opposed to how response spectra scale. We still have a problem when we talk about the word spectra. The engineers hear response spectra no matter what you say, and the seismologists hear Fourier spectra no matter what you say. And they behave differently. And it's actually easier for us to try to tie the seismological constraints and scaling in Fourier spectra. The other reason for doing this is going to be in empirically developing models with kappa in them is trivial in Fourier spectra and really difficult in response spectra because it depends on the shape of what's going in. So I think this is going to help us. I would say the real issue here is how much do you say move to simulations and we're ready to use them. And with these sets of simulations, they didn't pass our validation, so we can't use them yet. The long-term fix to that is make them work so we can trust the amplitudes in the east. And right now, the last time we met, I think the word was they were pretty crappy fits. It was Gail's technical term for what was going on. And given our schedule, they're not going to be fixed and improved yet for what we're doing. We did get Art's model for the full simulations, and that's looking better in terms of using it. But this actually works pretty well. The RVT that you'll hear later on is we calibrate it back from these simulation or these FAS models to the actual data as opposed to just working through theoretically what ought to match up. And so the model, it works. I guess I would agree it's somewhat pragmatic, but this is an easier way to deal with what the science says, how the earthquakes could scale in the way seismologists think about it, and then let's just still turn it into an engineering model at the end in terms of response spectra. So,
Christian.
Yeah, very quick, because the juicy part is coming. Yes.
Okay, very quick question. Is there anything for us to use right now? Because if you are not done with PSA, this means that it cannot be used today.
Not today.
Even for scaling.
The parameterized models aren't there, but all of the simulations are there in the way that what Jeff was talking about. So scale to magnitude 5, dumps of everything is there, but they're not yet fit and parameterized. But you could actually just check it yourself with with how your model scales compared to what those simulations say the response spectra should scale.
Okay, and where is it available?
We're going to share with all of you.
He wants to know where he can click on the file and get it today, and I
You can't. It's like 2 terabytes of data, so you have to wait for us to process it. But I haven't computed that yet. It's soon.
What I'm asking
1 week. 1 week.
Christine.
No, Yusuf is 2 weeks and 1 week.
Christine, the question is very simple. Where I don't need 2 terabytes of data. This simply scaling plots, if they are reliable.
They're not available yet. 1 week.
Okay, thank you.
Okay. Oh, I opened, what? That's the old one?
It doesn't matter. It's only changed like a couple sentences.
No, it's important that you feel good about your presentation. Let's take the right one.
I feel great about the old one, too.
You feel great about the old one? Okay, that's good. Ah, sorry. Yes, I did copy. Oh, it didn't sort. Okay, Justin Hollenbach, take it away.
So last meeting, Norm got up and said he was presenting a bunch of the work that I did. So now I'm presenting a bunch of work that Norm told me to do. So Art, when you have any difficult questions, I think Norm will probably answer them. But anyways, this is really a collaborative effort between me, Norm, Christine, and Nico. I've been working pretty closely over the last couple of months to develop this. So here we go. So I'm just really quickly going to go over, review the RBT approach, just really quick, go over the data that I am using to fit this model, just talk real briefly about the modeling that I'm doing, and then go into some details about the challenges that we've had in developing this model. And then we're going to look at what Jeff just talked about in an application, the large magnitude scaling, and then also adjusting the model to the VS30 of 3,000 meters per second and kappa 0.006. So again, the RVT approach, which I think has been hammered home pretty well here, but we're going to develop an empirical model in Fourier amplitude spectra. So all the engineers that's not response spectra, we're doing Fourier amplitude spectra. We're going to constrain how this scales with large magnitude with the stuff that Jeff just showed, so the broadband simulations. And then we're going to adjust this model to VS30 at 3,000, like I said, and kappa 0.006. So this is what I will be presenting on. And then Nico will give you a little bit of information about the duration model and RBT. And then what we get out in the end is a PSA model that hopefully compares well with other PSA models. So the, excuse me, the data that I'm using for this initial model, I'm only looking at data out to 300 kilometers for now. Obviously we need to get out to 1,000 kilometers, but for this initial presentation here, only 300. We're looking at magnitude above 2.5. There's quite a bit of frequency dependence of the data available that Christine alluded to, so a large majority of the data is TA, so above about 15 hertz. We have a pretty large fall off in the data that we have available, which is going to present itself as an issue. We also have this issue of the sites being a majority of the VS30s at all these sites have been assigned via proxy. So that'll also be something we have to deal with, and John gave a pretty good presentation on that yesterday of how we're going to approach that. And for now, we're excluding the Gulf Coast. So in the flat file, there's some quality flags. There's a quality flag based on some basic intensity measures. And just real quickly, those flags are either 0, 1, or 2. So 1 or 2 means there's some issue with the data, and I'm excluding all the data that have a flag of 1 or 2. Then there's a quality flag based on what are called quote-unquote data issues. This could be maybe a record that there was only analog recording and we didn't get it digitized or something like that. So I'm excluding all those that have a flag of number 2. I'm including all the USGS events that have been flagged as potentially induced, and we'll go over some of the differences that we see in those events. And then I've removed all the data that is within the microseismic noise window. I'll show some results in a second that show that the microseismic noise window potentially is not very well defined for some of the records, and so we do still have some noise getting in there, but we'll talk about that. So just real quickly to go over the regions that we're including. So this is region 2 in the flat file, so central U.S. and Canada, and we're including the Appalachians, the Atlantic coastal plain, and then all the crossing paths between those 3 regions. As you can see, we've explicitly excluded the Gulf Coast, and any data that stations that fall outside of these 3 regions or events that have fallen outside of these 3 regions. So the way we're doing this modeling, we're just really simple mixed effects regression with a maximum likelihood estimator. We're doing this frequency by frequency, so we're not assuming Bruin spectral shape or anything like that, just one frequency time. So we have some frequency-dependent coefficients that we're solving for. We're solving for frequency-dependent event terms, and then also this delta S2S term. So this is going to be the average deviation at a site from what the model is assuming is the site response. So here's the functional form that we're working with. Really, really simple. We just have a constant quadratic magnitude scaling. We have a geometrical spreading slope here. And this is for bilinear model, I should say. So we have this model for inside the hinge distance and then another model for outside the hinge distance. This is not magnitude-dependent geometrical spreading. We just don't have the data really to show if there's magnitude dependence in this or not. And I think from Yanye's or Emra's presentation the other day, that's maybe something we would see in PSA and not in FAS anyways. And then also a linear distance scaling and then a VS30 term. And this C6 term in here is our short distance saturation term. So we are not developing a model that is going to be able to scale with VS30. We're developing a model for 3,000 meters per second kappa 006. But we have to have this in here for the FAS development part to really account for all the differences in sites that we have, especially considering that we have a lot of sites that are assigned VS30s from proxies, so we need to take that uncertainty out. And so that's why that particular term is in there, but it won't be used in the forward sense. So just real quickly, the saturation term. So it's an along strike term to account for the saturation that we see in amplitudes for increasing magnitude and for close-in distances. We don't have the data to really constrain what this saturation term is, so we're just going to assume a couple different models and see how it affects our results. This is a plot of some various short distance saturation terms that we've considered. So just to go through them really quickly, this black line here is the Cho and Young's model from the NJUS2. Here, this constant term with magnitude is the Idris. Another constant here is Campbell and Besorgnia. And then these blue lines here, some of them are kind of hard to see. These are this kind of lighter blue, but not cyan, is just the ASK model. And then I had a couple variations on the ASK model. And then we have an Atkinson and Silva 2000 term here. And then the last one, this purple line, I simply took the Leonard length scaling with magnitude and just divided it by, I think, a third, and said, throw it up there and see if that could be of any use as far as the saturation term goes. In the magnitude ranges that we have data, there's not really a whole lot of difference between these models, but when you throw in a constant and a magnitude-independent saturation, that's where you see some differences. But we really have magnitudes down here, so there's not really a whole lot of difference in these models. So just to look kind of at how the short distance saturation term is going to affect our results, we really want to focus on close-in data, see how the residuals close-in are affected by these different short distance saturation terms. So what I'm plotting here is with frequency. I have the single station within event residuals, and the red dots represent the average for data that's within 20 kilometers, and then the blue dots represent the average for data that's within 10 kilometers. And this particular plot is for the Atkin and Silva 2000 model. And it'll hopefully make more sense when I flip through a couple of these, that we don't see a whole lot of difference between these plots when we change the short distance saturation model. So this is the ASK model, and just to flip back and forth real quickly, we don't see a whole lot of variation in how the residuals look close in when we change this model. And then if we go to another model, so say a constant model like Idris that's independent of magnitude, we see maybe a little bit difference, but really I think what's going on here is some other coefficients are compensating for when we change the short distance saturation. So again, this is going to be kind of difficult for us to really pull out of the data. So apparent, this used to say geometrical spreading, and then yesterday I changed it. This is the apparent geometrical spreading. And so here in our functional form, we have the slope inside the hinge, and then we have the slope beyond the hinge distance for our bilinear model here. And one thing that's also going to be difficult for us to constrain with this data is really where this hinge location is. So we're just going to try a couple different hinge locations and see in the residuals if we can really tell if one fits the data any better. And so for the next couple plots I'm going to show, I've just assumed the short distance model from Atkinson and Silva 2000, so we don't have any confusion there. So again, we're going to be looking at the within event residuals close in, binned for within 20 kilometers and within 10 kilometers, because again, the geometrical spreading slope within the hinge is really going to affect these residuals potentially. So this is for a hinge distance of 40 kilometers, and then we have a hinge distance of 50 kilometers, not that different. But when we push this hinge distance out too far, then we'll start to see some things going on. So when I change it to 70 kilometers, we see a little bit different, and then when I go all the way out to 100 kilometers, then we see some more shifting up here in the higher frequencies, which we don't like. I'm going to show some plots of what those slopes actually are. So the blue dots here are going to be the geometrical spreading slope within the hinge, and this is versus frequency. So again, we're regressing frequency by frequency, so we're not going to just plow through all these and fit one for the frequencies, for all frequencies. And then the red dots here are that geometrical spreading slope beyond the hinge. And so in here, for 40 kilometers, we're getting pretty steep apparent geometrical spreading at frequencies between about 1 hertz and 10 hertz. So in the order of minus 1.4 to minus 1.2, and then at higher frequencies, closer to minus 1, and at lower frequencies, we're seeing some deviations. And I think Art alluded to the difference in apparent geometrical attenuation as you look at different frequency ranges. So we're seeing this too. If I change this to 50 kilometer hinge distance, say for example, then we're going to make this geometrical attenuation within the hinge a little bit a little bit less steep, a little bit more positive. And then if I go out to 70 kilometers, even more. And then what we're seeing here is some really unrealistic values of the geometrical attenuation beyond the hinge distance. So this is pretty clearly not working for us. And then one step further to 100, we see things kind of blowing up and going out of control. So one thing we can do is just fix that geometrical attenuation beyond the hinge distance at minus a half. I think that's a pretty reasonable assumption based on the literature. And then go back and see what happens. One thing that happens when we let the geometrical attenuation beyond the hinge go free is we really get, again, some bad results on the slope for that linear distance term. So we'll get some positive slopes on the linear distance term, which, could be analogous to Q. It shouldn't really be going positive. This is bad. And then again, up at high frequencies, we're seeing some misbehavior too. But if we go ahead and fix that geometrical attenuation beyond the hinge to be frequency independent and just fix it at a minus a half, and this is for a 50 kilometer hinge distance. And then we have, again, some frequency dependence in the apparent geometrical attenuation inside the hinge. We're going to get a lot better results for that linear distance attenuation term. So we don't have any more positive values, which is nice, and we see a steepening here out at higher frequencies. So that's just some information on the geometrical attenuation and the linear R term. I'm going to talk about potentially induced events now, and what we see in those. So this is a flag that the USGS helped us out with. We did not assign this ourselves. I think if I don't know exactly how they assigned the flag personally, but I think that maybe Christine could elaborate that on a little bit if anybody is interested. The majority of these events are in Arkansas and Oklahoma. We have one in Ohio, and we'll show a map here really quick. Unfortunately for us, we don't have any tectonic events in the same regions, and I'll just show the maps. We don't have very many tectonic events in the same regions that we have the high concentration of potentially induced events. So we have one quote-unquote tectonic event here in Arkansas. It only has very few recordings, and they're not recordings in the same azimuthal direction as the recordings that are observed for these potentially induced events. So we're really sampling a piece of the crust with these potentially induced events that isn't really sampled by these tectonic events, and what we're seeing is some potentially regional differences in the attenuation that I'll show. So this is a plot of within event residuals at 10 hertz. In the red dots here, I have this is residuals that come from events in Oklahoma or Arkansas. The blue dots are for other Central and Eastern North America stations, not in Oklahoma and Arkansas. And then this blue line here is just the binned averages with different distances. The red line is binned averages with different distances for the Oklahoma and Arkansas events, and then this green line is just the binned average for all the regions. And we can see here misfit or offset in these residuals for Oklahoma and Arkansas events here, shifted down below the 0 line, and that's for distances within about 60, 70 kilometers. If we go out and look at some lower frequencies, so half a hertz, we see the opposite effects happening. So we see a bump up in these residuals for the Oklahoma and Arkansas region at lower frequencies relative to the rest of the data. We can also just take a quick look at the event terms. I could go back and regionalize this model and say, all right, I have a different geometrical attenuation or apparent geometrical attenuation for Oklahoma and Arkansas events than I do for other Central and Eastern United States events. But I want to look and see how that trade-offs with the event term. So here what I'm showing is the event terms with frequency, and this is for in blue we have tectonic shallow events. So those are not potentially induced, and my designation for shallow, I'm just saying above 5 kilometers hypercentral depth. And then again, I'm showing potentially induced events that also have a hypercentral depth of above 5 kilometers. And we see relatively similar trends at low frequencies for these events. And then at higher frequencies, we see pretty large deviations in their event terms. And I think this is analogous with the insinuation that potentially induced events have a lower stress drop than tectonic events. And that's again, something that we would see in the higher frequencies of the event terms. And if I look at deeper events, we're still seeing these differences at higher frequencies and at lower frequencies in the event terms with frequency. But now we could say, all right, well, what if I regionalize this? And I said I had a different geometrical attenuation inside the hinge distance for these two regions. We could maybe improve this, at least for the within event residuals versus distance, but then we would see some changes in the event terms with frequency that we should keep track of. So now I've regionalized this model, and I said that the geometrical attenuation for my blue dots is different than it is for my red dots. And we see a slight improvement here in this offset of the red dots relative to the 0 line for the 10 hertz data. And then when we go back and look at the 5 hertz or the 0.5 hertz data, we're not seeing quite as much improvement for that. But there's a slight improvement there, I would say. But then I think the important part here is to go see how this affects the event terms, because we're trading things off here. And now when I look at shallow tectonic events and shallow potentially induced events, and I plot their event terms with frequency, we're seeing a lot more similarity than we did before, both at high frequency and at low frequency. And then if I go back and look at deep events, again, we're not seeing the same differences. So I think that there's definitely some trade-offs here between attenuation, apparent attenuation, close in, and maybe stress drop. It's hard to really imply that stress drop is mapping perfectly into my event term, really. I don't think that that's a fair comparison necessarily, but I think we can at least have that discussion as to what's going on. Excuse me. So when I do regionalize this, these are the apparent geometrical attenuation slopes within the hinge distance that I'm getting out. And again, I'm just fixing the geometrical attenuation beyond the hinge distance at minus 0.5. And then at high frequencies, we're seeing the apparent geometrical attenuation for Oklahoma and Arkansas events is coming in steeper here than it is for these other events in central and eastern United States. And then above about 40 hertz, we're getting some more unreasonable results here, especially for central and eastern United States. We're saying, a positive geometrical attenuation inside the hinge really doesn't make sense. So we got to do something there. So the hypocentral depth, I think that the data suggests that there is a need for a depth parameter in our model that we'll have to put in. Depending on whether we regionalize apparent geometrical attenuation or not, it'll depend. The way we parameterize depth in this model will depend on whether we choose to regionalize the apparent geometrical attenuation. So that's something we have to make some decisions on still. Obviously there's trade-offs between attenuation, and you change something about the regionalized attenuation, it shows up somewhere else in your model. So we have to be careful about where we're putting things and make sure that what we're getting out is actually useful. So we'll talk about some low frequency noise that we're seeing, and then also the magnitude scaling issue that Jeff just talked about earlier. So at low frequencies, we're getting bad magnitude scaling. And this is, I think, the result of a poorly defined microseismic window. So we're taking out the microseismic noise where it's listed, where it's available, but we're still getting funny results. And we can't really use this magnitude scaling, and certainly can't extrapolate it beyond about magnitude 5 for frequencies below 1 hertz, or frequencies above 10 hertz, really. So this is the noise that I'm talking about right here. What I'm plotting is, so this is just a simple point source model. And these red data points are then the model that I use, and I'm predicting magnitude 2 event. I know, magnitude 2 is not, we're not obligated to predict magnitude 2s with our model, but I think it serves a point. At 50 kilometers for a shear velocity of 760. And if this was strictly a noise issue, then we would hopefully see these peaks coming up at the same level for different magnitudes. If I go up to magnitude 3, then we're seeing a bump up in this noise level here, and then at magnitude 4, it pretty much goes away. But what that's doing to my magnitude scaling is here. So this is the coefficient on the linear magnitude term, and I'm getting some negative slopes there on the linear magnitude term at low frequencies, and then for that quadratic term, I'm getting some positive slopes on the quadratic term. So that's going to cause my magnitude scaling to not be usable above magnitude 5, really. So that's an issue, and that kind of segues nicely into what Jeff was talking about, although I guess Art thinks we can't really use it. But what we're going to do is, instead of follow this magnitude scaling, we're going to take the magnitude scaling that Jeff talked about. And I'm going to flip through the next slides pretty quickly because Jeff covered it pretty well. So we're going to take the broadband simulations, and we're going to use, again, we don't trust their amplitudes, so we're just going to use ratios to get from magnitude 5 from our predictions up to magnitude 6, 7, 8, wherever we need to go. And so the way this is going to work is if I want to get a estimate for a magnitude above magnitude 5, I'll take a prediction at magnitude 5 from my empirical model, and I'll just slap on this ratio here. This is actually shouldn't be log. I apologize. It should be the log of this plus the log of that ratio. So forgive me for that typo. So Jeff showed these earlier, but what I'm using is only XSIM and Graves and Pitarka, and that's what I used to develop some models that I handed off to Nico, and he's going to show some results in PSA in a little bit. But again, as Jeff showed, we see some funny things going on for the other two broadband simulation methods, so we're just going to stick with XSIM and Graves and Pitarka for now. And so these are the coefficients that Jeff talked about. We're just fitting this log of the ratios to a simple quadratic magnitude function. Again, these are going to be the B2 terms, and then these are the coefficients on that quadratic term here in C2. And this is a function of frequency, so we can go ahead and just apply that to the model. These are some magnitude scaling plots, but again, Jeff showed these, so we don't need to dwell on them, but that's 10 kilometers, 20 kilometers, 50 kilometers at 0.5 hertz, and then out at 10 hertz, we see 10 kilometers, 20 kilometers, and 50 kilometers for the magnitude scaling. Blue is for XSIM, and red is for Graves and Matarga. So I can apply that to my model and get up to magnitudes that I need to get to. And then adjustment to hard rock. So we're going to use amplifications same amplifications that Bob and Walter are using right now for their inversions. At least preliminarily, we can always go back and use the amplifications that they back out after they're done. I think Bob alluded to iterating on those amplifications and not necessarily using the first pass, but making them a little bit better based on what the data is telling them. So we're going to use those to get to 3,000, and then what I've done as a first pass is I'm just visually going to inspect the high frequency shape of my model and pick what the kappa looks like, and then just simply adjust it with this host to target adjustment for the kappa values, and we're going to get to 0.06, and then I'm just going to adjust my FAS with these FAS amplification ratios. So the kappa, this is for a magnitude 4 at 20 kilometers, and again, what I'm plotting here in the red is just a model prediction that I have at that magnitude and distance for a VS30 of 760. And then these black lines are just point sources for different stress parameters, and just visually pick, okay, I can iterate on my kappa that I'm plotting up there and pick something that looks about right. So just as a first pass, we say 0.15 is what I plotted. It looks okay. Let's just run with that. And then take these amplifications. So they're using NEHRP site classes. I'm just, what I've just shown is 760, so the NEHRP BC boundary. So I can take a B site or a C site and try them both and see what works best. I think it would be better probably just to go back and change the amplifications that I use to generate these point sources, and then make a model prediction in the center of one of those NEHRP bins, and that would be more appropriate. But for now, that's not what I've done. So those are the applications, and then that's pretty much it. I take the empirical model, I adjust it to higher magnitudes, adjust it to appropriate hard rock conditions, and then we take the calibrated duration model and RBT, and we go to PSA. And again, Nico's going to show some comparisons of what the PSA looks like compared to other models. That's all I got.
You just went through this. Okay. Questions? John, Stu.
So you have a magnitude scaling based on simulations beyond 5, and you have a different magnitude scaling based on your analysis of the data below 5. How do those slopes match up?
Yeah, that's a good question. So it depends on the frequency. For the frequencies that I showed before where we have bad coefficients, negative coefficient on the linear term and a positive on the quadratic term, they don't match up very well at all. But on the areas, from about 1 hertz to 10 hertz where it's behaving better, they look okay.
So where there would be a bend, will you allow that in the final model, or would you somehow?
A bend, you mean? So if I use the magnitude scaling from my model to 5 and it has a strange kink that's not smooth,
right.
I think we just smooth through it. Yeah, that's what Norm's telling me we should do.
Okay, and then a different question is, I think I missed a detail in this 760 to 3000. So you do independent regressions at every frequency. And so then you can take your model, sample it at 760, and then you're inferring what the kappa is for that. Is that
correct? Yeah. I mean, so that was just a visual, but I think we can do something more formal and actually calculate what the kappa is numerically for a prediction from any VS30, and then apply the appropriate implications for that prediction.
So you think that's about 0.015, or that was just a...
So for that particular plot, I think it's about 0.015. But if we were to go back and do it for a specific VS30, I think we should, we're going to go back and calculate it and say this is what the slope is at the higher frequencies, and then we will get it like that.
I think, let me say, correct me if I'm not saying this right, but he's taken out the site terms, right, in the
Correct.
regression. So remember we were dealing yesterday with what about the unreliable site conditions and how do we deal with that? So every site has had its average site term removed. Okay, so now the question is, this is a model relative to what, right? Because the site terms have been corrected. So he's got it relative to whatever the sort of average VS30 is of the ones that are maintained. And did you left everything in there at this point? Did you remove the unreliable or questionable sites?
No, I've left all the sites in there.
So he left them all in there. We would probably go back and do it throwing out the questionable ones, because the nice thing about this is the correction is not for individual sites, rather the correction is for the average site condition. And we know the average a lot better than we know the individual ones. So that's why we can get a simpler model for what the correction is. And we can choose a subset of the sites that are, or at least, let's say, put aside the ones that don't look like we have the right scaling in them, so because their VS30 may not be representative of the average.
Right, and that's the list that we can give you.
Correct.
Did you just say that you've subtracted the delta S2S? Or you will in the future be doing that? It hasn't been done yet.
He took it out.
Yeah, it's part of the model fitting. So when we're going in here, we're solving for coefficients and these terms, so it's not in the median model, right? We're taking it out of there.
Right, and then the spectral shape that you'll use to compute kappa is from the model at 760.
It's from the model wherever we think it is appropriate. So whatever the average site that Norman was getting at is.
Okay. May not be 760.
Yeah, it might not be 760. It could be. I haven't looked at the data closely. For the data inside 300 kilometers, a lot of the frequencies have an average VS30 that's above 760. But when we push that out to further and further distances, you're picking up more and more stations that, TA stations or stations on softer soils. So that'll bring the VS30 down a little bit, but I don't know what it is now.
But whatever value it is, you need to have a theoretical amplification from 3,000 to that number.
Correct. Yeah. So initially I just used what Bob and Walt are using, and then they're going to take a look and see how good their amplifications are doing for the east. And we can go back and use whatever they update their site profiles and their amplifications to be. Or, we don't have to use what Bob and Walt are using either. We can pick something that's better or different, maybe not better, but different.
Okay.
Yes, you have your mic. Gabe? Oh, somebody took your mic. Oh.
Your TI.
So higher up that's right, in the pecking order. So one note on your comparison of the additive depth terms that you were doing early on. Those are apples and oranges to some extent. So, for instance, they are coupled with how the, quote, geometric spreading is included in the model.
Right.
And one of the reasons, for instance, that CY14 is much larger than the others is we fix the geometric spreading to have a high coefficient of 2. So they're coupled together. So it's difficult to look at that and make a judgment about what numbers should be coming from those and how they enter, because some of them enter just additive and some of them are squared together in square root. So the plot may not be that informative.
All right.
Yeah, just one comment on the site application factor. Following up on John Stewart, are you looking at alternative ways to estimate those factors? Other than the log VS30 terms, for example, what Gail has done, we did a couple of approaches in the 2013 work, and there's probably many others out there.
So for our model, and considering the sites that we have as far as our characterization goes, they're very unreliable. I think that the log VS30 term is probably the best that we can do right now. We're not going to try to make it overcomplicated. If we had better characterization then maybe we would try that. But right now, I think that's probably as good as we're going to do.
I think you're right. I
don't know, maybe Norm wants to elaborate on that.
I think, maybe first of all, the problem is the mischaracterization of sites, not.
I mean, it's not even necessarily strictly mischaracterization, but sites that we don't know exactly how they're behaving. There would be sites that, shallow or stiff sites where we have resonances or things like that. The log BS study just isn't going to pick up, but we don't have the characterization really to say what kind of sites they are.
If we go back on the depth dependence, did any of the other analyses, any of your scales, or see a depth term in terms of, like a depth-dependent stress drop or something? But is there a depth dependence in the model that would be built into it?
A depth dependence in what part? We clearly have a depth dependence in the saturation term.
Thinking of a scaling like a stress drop term. So is there something that you would say, like what Jack had, Boatwright had in his depth dependence of stress drop, we would fit that into the median model?
Yes, we do have a depth dependence of stress drop in the model. Right, so we have the stress drop, and it was in one of Emra's slides yesterday. We've got the stress drop increasing as a function of depth up to about 10 kilometers, and then it's constant above that. And we have the same model in the west and the east, and the east one is just shifted up relative to the west.
And that depth term, one thing we have to straighten out is what is it? So is it hypocentral depth even for larger magnitudes? Yes. Yes.
Yeah, so just to follow up on that, when we look at event terms with depth, for higher frequencies we see trends at depths about less than 10 kilometers, and then again constant for out to beyond 10 kilometers. So that's relatively consistent with what we're seeing.
Justin, you've done a great job. No questions. Okay.
It's because I've confused everybody.
No, it was really good. Thank you.
Okay.
Okay. Okay, our last presentation before lunch. You want the full view?
Oh.
Full screen.
No.
No? Oh, you need to do something. Okay. So while Nico is doing something, what do you need to do?
No, it's okay.
Good?
Yeah.
Okay, he's happy. Nico is going to talk about the duration model and how it's used for FAS, and it's empirically derived, and show the PSA final model.
All right. So basically, what I'm going to do is wrap up the peer model and just talk about the final ingredient that we need to go from FAS to PSA, and that's the duration. And so we need the duration to calculate the response spectral values, and there are several duration measures measured in the literature, like D5 to 95 or D5 to 95 prime, D5 to 75. But if we just want to predict PSA, we don't really care about the actual value of the duration. All we care is about the fit to the PSA. So therefore, what we're going to do is we're going to choose a duration that provides the best PSA prediction given the FAS. So basically, we're going to turn the duration into a parameter of the model, and then we're going to model that parameter. So this is the basic model that we have. Albert talked about this, and so this is how we go from the FAS to the response spectrum, and so we have a model for the peak factor, and we have and that's where the FAS comes in, and then from that one, that requires an estimate of duration. And what we're just going to do is we're going to invert for that duration. So basically, we're going to turn duration into a parameter. And the misfit function is just least squares. So basically, the input to our inversion is the downsampled and the smoothed FAS for each record, and the PSA for that record, and then we're going to calculate the PSA given RVT, given the peak factor, and given all these assumptions that we have. What that means is that the duration that we get out of is not a physical duration. It's a parameter of the model. But this parameter depends on magnitude and distance of the record. It's a bit like the near source saturation term, which in Justin's presentation, which was magnitude dependent. And now we just have a different parameter, which is magnitude and distance dependent, and maybe it has some other dependencies. And so basically I'm just trying to, on this presentation, I'm going to show how we're going to model that. This is how the inversion looks like for two records. I don't really know if you can see the colors, but basically we have a black line, which is the PSA calculated from the time series, and then we have a red line, which is the PSA calculated from the FAS and in inverted duration. So there's some misfit between those two. It's just because we cannot explain everything, but what we assume is we're close enough. What I did, so I calculated durations for the NGA East data set, so basically for the last flat file that we had, and this is how the data looks like. So this is magnitude versus log duration, and this is distance versus log duration. And as always, we have the problem here. We have the problem in the large magnitudes. So we're not going to find a good model that extrapolates these duration parameters to large magnitudes. So what we're going to do is we're just going to expand the data set using the same duration parameters from the NGA West 2 data set. So I calculated for a subset for about like 1,400 records. I calculated durations in the same way as for the East. And then we're just using those data together to build a model that's hopefully going to extrapolate well. So in the NGA East, we have about 8,500 durations from 75 events and about 1,200 stations. The largest event is Nahani, that's magnitude 6.8, and it only has records within 20 kilometers. So that's not enough to constrain the magnitude scaling. From the NGA West 2, I used 1,440 records from 229 events and 850 stations. And I chose those records to have a good magnitude coverage, so to have both coverage in the small magnitudes, but also to expand to large magnitudes. So in the small magnitudes to compare to the Eastern data set, but also then that we can expand it to large magnitudes. And the distances are chosen to be from 1 to 250 kilometers, also to have some overlap with the Eastern data set. And we might have possible differences between the East and the West. We're going to resolve these differences by using a random effects model. So basically we have random effects for regions. So the parameters of the model are regionally dependent. The models that I considered are shown here. So there's basically several models in the literature how you would model durations, and I'm going through all of them. The first one is like this. That's what Camden and Stewart used, and they have the log duration is the log of a function of magnitude, distance, plus a function of distance, plus a function of the site, and then plus some between event, within event, and station-to-station residual. The other one is, so that's in essence an additive model. So if we take it to the exponent of E, then we have duration is a function of magnitude plus a function of distance plus a function of source. We could try to model this directly by saying duration is just a function of magnitude plus a function of distance plus a function of some site parameters and their respective error terms. Or what's been done in Bommer et al. 2009 or in Bohrer et al. From 2014, we could use something similar to a PSA GMPE, which would correspond to a multiplicative duration. I'm going through all of these models. The problem I have with this model is if you actually take the exponent, you have the duration is your function of magnitude times your between event residual times your within event residual times your between station residual. And actually these should all be to the exponent of E. So that means your site residual actually affects your, would map into your source duration. That's why I did not use this model. The problem with the next model is that these error terms are not normally distributed. So we would have to model them as something like log normally distribution, and then the problem is it's the sum of two log normal distributions is not a log normal distribution anymore, so that becomes really complicated, especially if we want to further subdivide the error term, for example, into station terms or into regional terms. So that leaves us with this, which is very similar to a GMPE. And the nice thing is, again, that these terms are normally distributed, so that means we can just add them. And it fits the data. So it fits the duration parameters that I have, so that's why I went with it. So this is the model that we have. We have the log duration is a function of magnitude, which I don't want to call it source duration, but it would correspond to something like that, plus something that's a function of distance, plus maybe a site function that we didn't use in this case. And then we have the error term, so that's between event residual, within event residual, and site-to-site residual, that's delta S. And all of these are normally distributed. The functional form looks like this. It's very, very simple. It's just a linear magnitude term and a linear log R term. And to account for regional differences between the east and the west, we're going to assume that the coefficients are regionally dependent. So that means in addition to these random effects for events and stations, we have random effects for regions. So that's shown down here. Each regional parameter is something like its mean plus some regional adjustment. And we assume that only A0 and A2 are regionally dependent. The reason to not have A1 regionally dependent is that it defeats the purpose of letting the eastern data constrain the large magnitude scale. And what's important, I'm only using two regions. I'm only using east and west. So I'm not subdividing the east or the west into a further region. And that it actually works pretty well. Okay. How we do the regression, the problem is most events are small, and they're at least in the east, and they're recorded at larger distances. That means the source terms are pretty small, and they're very small compared to the path terms. That means it's really hard to constrain the between event residual or the event residual. So therefore what we're doing is we're doing the regression in two steps. First, we're just doing a regression on the data up to 50 kilometers to fix the magnitude scaling. And then we use that magnitude scaling and the event terms we get out of the first step to regress or to invert for the rest of the parameters. And the regression is done using Bayesian inference, and we have some priors on the parameters, which are for the coefficients, they are normal distributions, and for the standard deviations, they are half Cauchy distributions. It's not very sensitive. We have a lot of data, so it's not very sensitive to the prior distributions. This is just how the fit looks like. So this is the event term and the event residual. And in this case, I define the event term as the magnitude scaling plus the between event residual. And as we can see, it's very nice. It's a nice linear relationship. And so that's the residual versus magnitude, and there's no trend to see.
The red is the east?
The red is the east, as before, and the blue is the west. Right. So basically what we're doing, so this is the first step, and then we're fixing A1, and we're fixing delta B for the events that we have. And then we use that in the second step to calculate residuals. These are color-coded, the event residuals, by region. So that's red is the Gulf Coast, and we might make the case that they have larger residuals. So it might be reasonable to include an additional random effect for the Gulf Coast. And the other ones are the regions, most of them are the regions for the West, and there's no general trend to see, because most of them only have very, very few events. This is a plot showing event residual of the potentially induced events, and the red dots are the potential induced events. And there's also no difference between the potentially induced events and most of the other events to see. This is then the second step. So this is how the within event residual looks like, so delta W. And oh, I messed this up again. So this is the station-to-station residual. So that's delta S versus, oh, that should, oops. This should be versus VS30. So there's no trend in we don't see any trend with VS30. That's why it's not in the model. And here we don't really see a trend in the residuals with respect to distance. And the next one here we have the magnitude dependent within event residuals. So this is for magnitudes 4 to 5 and magnitudes 5 to 6. And here we have 6 to 7 and 7 to 8. And we don't see a trend, we don't see a shift up and down, which is good, so which gives us confidence that we can actually use the extrapolation to large magnitudes in this case. So now we're going to use we don't really care about the durations, we care about the PSA. So we need to convert FAS to PSA using the duration model, and you know how that works. So what we're going to, the input to the conversion to PSA is the mean FAS and the mean duration. Since both of them are modeled as log normal distributions, we need to convert the median prediction to a mean prediction, which is just very simple based on the statistics of the log normal distribution. And these are residuals of PSA given Justin's model predictions and given predictions of the duration model. So this is for 1 Hertz. Event event residuals versus within event residuals, we don't see any trend. There's a slight bias, which I don't really know where it comes from. This is for 5 Hertz, and this is for 10 Hertz. And again, we don't see any real trend between the PSA model predictions based on the FAS model and the duration model and the time series calculated PSA values. And this is then how the extrapolation to large magnitudes that Jeff and Justin talked about looks in PSA. So this is predictions for magnitude 6 at 5 Hertz, and this is at 100 kilometers at 5 Hertz, and this is PSA versus distance and PSA versus magnitude, using the different simulation methods to extrapolate. So in this case, red is Grayson-Pitaka and blue is XM. And they lead to quite different results at magnitude 8. So basically what we did, we treated the duration as a parameter of the model to match PSA via RBT. The magnitude scaling of the duration parameter is constrained, and the distance scaling is constrained by Western data, and that works pretty well. And we have a multiplicative model which fits the data. What I haven't done is to see how the uncertainty of the duration model impacts the PSA predictions. So basically take the uncertainty in the duration model parameters and then see how that changes the PSA model. I've done that using a preliminary FAS model and a preliminary duration model, and the impact of the duration uncertainty is pretty small. The other thing that I think we should do is calibrate the model, or calibrate the duration against the model FAS. So right now it's calibrated against the record FAS, but we're using it together with the model. So to get a better fit to the PSA, we should actually calibrate it against the FAS model and not against the actual data. And the other thing is, it might be worthwhile to use a regional model for all different regions. So not only East-West, but only include Gulf Coast and maybe even include the Western models. That has the additional benefit that it gives some better statistics of the random effects. And that's it.
Okay, are there any questions for Nico? So I see, a flurry of hands on that side. So let's start with Art.
Maybe I missed this, but did you look at the effect of source depth on a duration?
I have looked at it. It's very small, so that I haven't included it. I might include it. It's very small.
And I would expect like Eastern U.S. sources at the same magnitude would have more compact sources, so less duration compared to the same magnitude in the West. Is that something you see?
Yes.
Okay, we had Ken Campbell, then John Stewart, Albert.
Well, actually, I think I'm asking the same. This is Ken Campbell asking the same question Art did. So Dave Bohr suggested that durations were longer in the East than in the West. So I was curious what your regional. So you had two regional factors in there, right?
Right. So
the overall magnitude scaling with.
So the overall magnitude scaling is not regionally dependent. Just the bias term is regionally dependent, but that leads to slightly less larger in the West. But due to the distance term, you actually get longer durations in the East.
Oh, okay. So, okay. Thanks.
So my question concerns that bias that you showed in the between event residuals for PSA. It looked like it was about 10 to 20%.
Yes.
So that means that at the end of the day, if you predict FAS, you combine it with your duration model through RVT, you end up with a spectral acceleration that is too low by 10 to 20%.
Right. We haven't figured that out yet.
Yeah, so that's not
that's
good.
a concern.
Yeah, that needs to be fixed.
But Nico, you want to talk about the conversion from
What?
median to mean? That we didn't consider all the statistics that might not take care of the whole 10%.
Yeah, one comment though, that may be, if there is a lack of fit in the peak factor, I think it will show up there. Now, if the peak factor is not perfect and it starts failing at 1 hertz, then you might see a bias there. Might be the explanation for the bias.
So you see, which bias was John talking about? This one?
That is this one. That will basically the mean of the between event residuals is about here.
But at higher frequencies, you don't see that.
Yeah, we don't see it at 5 hertz, but we see it
at 10 hertz.
A little bit there at 10 hertz.
Did you look at lower frequencies than 1 hertz?
Not yet.
Okay.
But,
if my hypothesis is right, then it'll be even worse at 2 seconds or so.
Nico, Albert Gautier. Nico, did you evaluate, when you said the VS30 was not important, did you evaluate east and west independently there? Or did you group them all together and then evaluate VS30?
That was done altogether. So there's no VS30 scaling in there. So that's why...
So you said that VS30 scaling wasn't important?
Yes.
But I think that may be because the VS30 classification for the east is struggling.
That should have been taken care of in the delta S term, so in the side-to-side coefficients, and we should see it in the side-to-side residuals. And we don't.
Okay.
But you're right. If there were a VS30 scaling in the model, it should probably be regionally dependent. It might actually, in that case, it might even be worthwhile having the sigma, so the side-to-side sigma regionally dependent, so because you just have less confidence in the east than in the west.
And then one other point, you mentioned that the normal by doing the functional form as you did it, that it's normally distributed.
Yes.
Assuming that the duration is log normally
Assuming that the duration is log normally distributed.
But you've not tested that yet?
I've tested that, and it looks normally distributed. The linear duration is certainly not normally distributed, and that just makes it hard to calculate the linear duration model.
Sorry, thanks.
Yeah, one question, and sometimes this is knowledge, sometimes it's bias. But therefore, is there a strong physical argument for the duration being a linear function of distance? Do you think?
Please ask the question again.
Is there a physical rationale for the duration being a linear function of distance? You mentioned that it was proposed by Paul Herman at one point, probably based on...
No, this is strictly based on looking at the observations and just subjectively coming up with a set of lines that would approximate the dependence on distance.
Okay,
it's completely arbitrary. The fact that we've used for years just segment, a bunch of little lines. And the trouble is, whenever you do that, because you have a kink, when you do predictions of ground motion versus distance, the kink is going to appear in your simulations. So it may be an unfortunate choice, but it's a very easy choice to implement.
Okay, but there's no big loss in abandoning that.
What?
There's no loss in abandoning that linear function.
Right.
Okay.
And this is not a duration of a signal. This is a parameter that goes into RVT that makes the Fourier spectrum.
But they should work. They don't have to be identical, but they should more or less follow the same trends.
I think they will. This is Gail. I think they will follow the same trends, but I think they could be a long ways from identical. And the key is what Norm just said, that it is not a duration measured from a signal. And I'm wondering whether we should even give it a different name to avoid confusion.
Could I enter in?
Just like we use, pseudo depth or fictitious depth for this saturation term. Maybe we should call this
effective duration, duration parameter,
pseudo duration, or something like that. It's not, because if you think of other things, like I think in the model that Emra and I have, where we ended up with a calibration constant, essentially, a mismatch between simulations and observations being closed by a constant term. Any constant term that's there is going to map in this method into an offset potentially of some kind in this duration function. So maybe we should just give this thing a different name to avoid confusion and avoid people doing things like taking the actual duration, 5 to 75% from this signal and that, and putting it on top of your model and saying, well, look, your model doesn't work. It's nothing like this at all.
That's something that's also important. This duration is tied to all the assumptions that went into the previous model. So it's tied to the exact same downsampling of the FAS and so on to the exact same peak factor. So that's
right. It's essentially a calibration factor that takes the place or holds the position of duration.
Okay, maybe we should call it D-NICO, or we can
no. You should call it
or DRVT. I'd like to point out that in my implementation of random vibration theory, I actually have two durations. I have one for the RMS and the other one that actually is used in the RMS to peak factor, and they're different. And so it's really important, as you were saying, to keep in mind that there are different durations.
We could use different durations and I've compared that. I've used the model you did with Eric. You get basically the same fit to the PSA. You just get a different duration, but which is then tied to using that particular model. But it works as well.
Okay.
Okay. What a beautiful time for lunch. Thank you, Nico. So let's go to lunch, which is 10 feet away. Oh, by the way, I forgot. So, Vladimir, so especially for you, all the ratios of Fourier spectra have been shared on the Dropbox of the working group, the GMP working group. It's raw. That's what we have. It's all the data we have as processed by Jeff, but not parameterized into a model. Not PSA yet. That's the 1 week. We don't have it. I don't have it yet. Thank you.